Okay. Okay, good morning, everybody. Thank you for coming to this IAU symposium. Welcome to South Africa. This is the first African IAU, and it is also the southernmost IAU General Assembly by a few kilometers, because Sydney is a little bit north of here. So the key topic of this symposium is the multi-point perspective of solar studies and solar and heliospheric studies. And this decade, the 20s, gives us a new perspective on solar physics and on heliophysics, because there are many observatories which added the already known observatories like SDO, like Hinode, SOHO, and Stereo. So now we have PSP and Solar Orbiter that are orbiting the sun, so giving a different perspective view of the sun, and an almost full view of the sun in some during some part of the orbit. And then we have the new solar observatories from China, SOS, and from India, Aditya. So this is, I think this is a very good breakthrough of in the study of the sun, and also in the understanding of space weather, how the sun interact with the rest of the solar system. So here in this symposium, we will see some of the results of these missions. And also we will discuss about the future perspectives, what we need to do. So far, there are good results about the connectivity between what happens on the sun, so all the dynamic and active phenomena, and what we measure in situ, so by the instrumentation that is flying with the spacecraft. And so we are. I think this will be an interesting symposium. Let's see. So I just stop here. I'll give the floor to Lee, that will give you some details on how these sessions will work, how to speak. And so let's try to stay in the time, of course. So there will be a chair to warn you, and also lights over there. Okay, welcome.
Welcome to the session. Just before the session starts, some reminder that there are 3 lights here. The green stands for the presentation starts, and the yellow 5 minutes left, and the red is the end of the talk. So the first talk will be given by Stephanie Yardley, and she will talk about solar orbiter and the PSP, multi-messengers of the inner heliosphere. Let's welcome.
Good morning, everyone. My name's Stephanie Yardley, and I'm kicking off the session here. Thanks for the organisers for giving me this opportunity to be here in Cape Town. And so today I'm going to talk... Yeah, is that better? Sorry, it's hard to hear up here. So today I'm going to talk about synergetic science between Solar Orbiter and Parker Solar Probe. Thank you. And in particular, I'm going to focus on studies of the solar wind and also of eruptions from the sun. Does anyone know? No, I need to... Next slide. How do I get to the next slide?
Next. Then the point is the green one.
Yeah. Oh, it wasn't working. Right. Thanks. So to start off, I'm just going to talk a bit about Parker Solar Probe and Solar Orbiter for those of you who aren't so familiar with the missions. So Parker Solar Probe was launched back in August 2018, of course, was named after the late Eugene Parker, and he was the first person to ever see a mission launched with his name. It's also one of the largest, closest objects to the sun, going within 6.2 million kilometers, so within about 10 solar radii at closest approach. And it's also one of the fastest objects that we have in space. And so it has 4 instruments on board. One of them, which is a remote sensing instrument, the others are in situ instruments. And the main goals of Parker Solar Probe are to understand more about the coronal heating problem, the acceleration of the solar wind, and also more about solar energetic particles. And so, of course, it's getting this close approach into the solar corona. It's something that we've never done before. Then on the other hand, we have Solar Orbiter. So Solar Orbiter was launched in February 2020, so 2 years after Parker Solar Probe. And again, we'll get close into the sun, but around 42 million kilometers at the closest approach. So this is about 0.29, 0.28 AU from the sun. And it's one of the most complex observatories ever built. It has 10 instruments on board, 6 remote sensing, 4 in situ instruments, in order to connect what we observe at the spacecraft back to the source regions on the sun. And of course, it's not long from now that we'll start to get the inclination of Solar Orbiter, and we'll start to see the first images of the sun's poles. And so Solar Orbiter has many goals that are in a line with Parker Solar Probe, but we're also going to be able to study more about the solar dynamo by looking at the poles. And so it's these unique orbits of the instrumentation that we have that allow us to get these amazing observations and then to tie them to the spacecraft. So I can't talk about Parker Solar Probe without talking about switchbacks. We've seen these before in the Ulysses and Helios data, but one of the big surprises about Parker Solar Probe was the ubiquitous reversals. So the switchbacks are the reversals in the magnetic field that we see. We also see these velocity spikes accompanied with these reversals. And going close into the sun, we managed to see a huge amount of these, and this was a big surprise. But not only do we see a huge amount of these switchbacks, they are accumulated in patches, as you can see here with the red lines underneath the velocity spikes. And it is thought that these correlate with the similar scales compared to supergranulation on the sun. So you can start to see this connection between maybe the source of the switchbacks moving through into the solar wind. We've now also observed them with Solar Orbiter. So now you're looking at the extreme ultraviolet with EUI, full sun. And then you've got the METIS data. And here you can see the S-shaped switchback in the corona. So this is one of the first observations of a switchback in the corona. And so there have been many theories, as we'll see in a minute, behind the formation of these switchbacks. And in this particular case, it's suggested to be this interchange reconnection between the open and closed magnetic field regions, because this switchback in particular was observed above an active region where you get this closed field next to open magnetic field. So as I mentioned, there are many different theories where the switchbacks actually come from. Are they formed close into the sun? Are they formed further out? Is it this reconnection or the interchange reconnection between open and closed magnetic field? Does this create a kink? Is it more like a flux rope? Are they formed by turbulent? Because these are quite turbulent structures. You can see the alphonic turbulent nature of these structures. Or is it something more to do with the Parker spiral itself? And so I feel to understand more about these structures, what we really need to do is tie observations of the source regions that we think that they come from to the in situ measurements that we get. And so we started to do this with Solar Orbiter. So because of not only the unique orbit of Solar Orbiter, but also the fact that we have these partial disk instruments on board, the remote sensing ones, we have these perihelion windows where every 6 months you have about 3 times 10-day windows of observations. And so they have to be planned meticulously in advance. And so during the first perihelion back in March 2022, we one of the first observations being on the slow solar wind. And so we call these SOOPs, the Solar Orbiter Observation Plans. And these took place during the first 2 remote sensing windows. As you can see here, there's the orbit of Solar Orbiter over this 6-month period. And so we had some observations that took place along the Sun-Earth line and then slightly off the Sun-Earth line, from about 0.5 to about 0.3 AU. And so the goal of this particular observation plan was to look at this, the release mechanisms of the slow solar wind in particular at the open-closed magnetic field boundaries. And therefore, the targets for this were active region boundaries and coronal holes, where we think we get this interchange reconnection taking place. And so in order to plan and also to analyse the data afterwards, we have to understand a lot about the connectivity, essentially tying what we see at the spacecraft in situ back to the source region on the sun. And we do this by modelling the magnetic connectivity. And this is a tool that we use where we tie a coronal magnetic field model with the interplanetary magnetic field. And so these are quite complicated observations to plan, because you want to be pointing at the source region of the solar wind you're going to measure at the spacecraft a few days later. And so here are some of the resulting observations. You can see the full sun image here by EUI. And at this particular moment in time, in March 2022, we were on the solar disk. We had a coronal hole and multiple active regions in a complex. And so the magnetic connectivity of Solar Orbiter using the tool was seen to move across these 2 regions. And so because for the majority of the period, we're actually connected to the active region, this is where we pointed some of the partial disk instruments. So now you'll see the high resolution image from EUI. You can see these nice open coronal fan loops. And we also had the SPICE instrument that can look at the composition of the regions and tie this to what is measured in situ. And so what did we actually observe during this period? Well, in the end, we got all types of solar wind. So we ended up with fast solar wind, followed by alphenic slow, and then slow solar wind from the large coronal hole that was on the near disk center, and then the 2 polarities of the active region. And we came to this conclusion because of the various different measurements that we were able to take using Solar Orbiter and the in situ measurements. So what you'll see here is we've looked at the solar wind speed from PASS. You then have the magnetic field from MAG, the radial magnetic field. And so we can see that the orientation of the magnetic field is inwards, pointing towards the sun, which is consistent with the negative polarities of both source regions. We also have, of course, periods where you can see patches of magnetic switchbacks, which I spoke about earlier. And then also we can look at the electrons using the EAS instrument, and essentially looking at the electron strahl, because these are essentially field aligned and can be a direct probe of the connectivity. And so what you'll see for the majority of the period, you have the 180-degree pitch angle. So we're seeing electrons streaming anti-parallel and outward along the magnetic field, consistent with one single source of open magnetic field, which we expect from the coronal hole. And then in the middle, you see in this black box, this period of the bidirectional strahl, where we think we're crossing the overexpanded closed loops of the active region. So we're actually crossing the 2 sources. We then looked at the composition using SWA HIS. And then we can see this trend where we go from looking at the iron oxygen, we can see the photospheric composition consistent with the coronal hole. And then we see the increase to coronal and then back to photospheric again. And then if you compare this to the observations taken by SPICE, then you can see that there's a difference, this spatial difference in the in the composition between the two regions where the connectivity points are situated. And so this this transition from the first to the second active region matches what we measured in situ. And then again, looking at the charge state ratios, we can see this increase. So we're seeing an increase in the temperature of the plasma. And so those were some of the first results from the slow wind soup. There are actually 4 runs of this soup, so the analysis is still ongoing, but there have been some other publications if you're interested in these particular studies. So during this period, it was actually Parker Solar Probes encounter number 11. And so we could actually measure so Solar Orbiter and Parker Solar Probe were actually measuring solar wind from the same regions. In particular, there was a couple of fast solar wind streams. We crossed the heliospheric current sheet and then also slow alphanic solar wind as well. And so if you look at the bottom right here, you can see the long latitude of the connectivity points, and actually Solar Orbiter and Parker Solar Probe are kind of going in different directions and crossing these different streams. And so it was interesting to see that the composition and variability of these periods were actually similar at both spacecraft. Although looking at this particular coronal hole, so this is the one that was, can I go back? So looking at this particular coronal hole, from the other study where we saw the coronal hole and the fast wind from the coronal hole initially, we found consistently that there were not only the same composition, but you also had the high alphanicity that you'd expect. So if you look at the cross helicity at the top, you can see this high alphanic flow from this coronal hole. But the only difference is we saw a lower alpha to proton abundance, which is not expected of coronal holes. And so this is one particular encounter. We need to look at different encounters and looking at the different conjunctions at different radial distances to look at the different properties of the solar wind. And that's what we're starting to do now. So there was the slow solar wind observations. Now we have the fast wind soup that has just started to run in the last perihelia. And so this was during October 2023. So you can see the EUI a high resolution image here. And I think this is should play as a moving. And actually the coronal hole that we were looking at, so now because we're focused on the fast wind, we're looking at the center of the coronal hole, and it's actually quite a dynamic place. And if you look at the plot next to it, you can see, looking at the in situ parameters, that you can indeed, similar to last time, you can see the fast wind from the coronal hole. And then looking at the configurations of the spacecraft, you can see that although not necessarily totally radially aligned, Parker Solar Probe and Solar Orbiter are roughly similar distances. And so we're starting to look at the 2 sets of data to try and make a comparison between them. There was also the most recent perihelion, which took place in April 2024. And you can see that Parker Solar Probe was at about 0.1 and Solar Orbiter was really close in at about 0.3. And so we're actually currently looking at the observations from this particular window where we're connected to a coronal hole. And we're starting to see that between Solar Orbiter and Parker Solar Probe, there are actually similar signatures, at least in the velocities there. So this is currently ongoing work. We're trying to put all the observations together. It takes a lot of time to put them together and analyze all the observations. And so now I want to move on a bit from talking about the solar wind to talking about solar eruptions. And so we had this case, this was in September 2022. And this was on the far side of the sun, where a solar snake slithers across the sun. So you can see here that if you look at the configuration of Parker Solar Probe and Solar Orbiter, you've got Parker Solar Probe on its close encounter 13, and then Solar Orbiter's further out at about 0.7 AU. And so Solar Orbiter was actually providing synoptic observations in support of this Parker Solar Probe encounter. And so what you can see, hopefully, is this snake-like structure move across the sun. And so what this is plasma flows that are flowing along what we think is as a flux rope that is present there before it eventually goes on to erupt. So of course, there's this question of, does the flux rope form before eruption? And if so, what's its handedness? How many turns does it have? And so in this particular case, they're able to see this right-handed flux rope through these plasma flows. So this flux rope extends from the active region all the way out into the quiet sun. And it had a right-handedness, so it was positive helicity with about 1 turn. So when this structure eventually erupted on the 5th of September, we could see it with the WISPR, the wide-angle coronagraph, which is on Parker Solar Probe. And so what you'll see here is as Parker Solar Probe is getting closer and closer to the sun, I think it's about 13 solar radii, when this structure erupts, you can see this is really where you see the nice complicated structures that we can now see with WISPR and also with the METIS coronagraph. So you can see the flux rope passing over the spacecraft. And so it is indeed detected by Parker Solar Probe. So you can see the magnetic field by fields in the top and the different components. And what you see is this really nice rotation in the radial magnetic field indicating this flux rope structure. And then in this particular paper, what they did is they used this magnetic helicity PVI technique to help identify the flux rope. And so not only did they manage to identify where the flux rope is hitting Parker Solar Probe, but also what you can do is, if you look in the bottom panel, you can look at the magnetic helicity and see that this is positive, which matches the orientation that we saw at the sun. It's also quite a complicated structure, and this is thought to be because not only was the solar eruption, the CME hitting Parker Solar Probe, but this eruption was very close to the heliospheric current sheet, which Parker Solar Probe was also passing at the time. So we see this very complicated structure that was measured by PSP. We've also seen, so not just on the far side, but also close in, we've seen Solar Orbiter acting as a space weather forecasting monitor. So we've had times where Solar Orbiter has been about 0.5 AU between the sun and the Earth. And we've had these two cases here, which was, again, I think back in 2022, March 2022, where two eruptions came from the sun, and we were able to measure the orientation of the magnetic field that was measured by Solar Orbiter. And this was about 40 hours before the eruption hit Earth. And so we could tell what the orientation of the flux rope, which stayed relatively similar when it was measured at Earth, giving us a lead time of about 40 hours in terms of the BZ, because obviously this is a big problem, being able to predict what the magnetic field orientation is at Earth and whether it's going to drive a geomagnetic storm. And so in this case, although normally you get a significant evolution between the sun and the Earth, we see that the magnetic field structures are very similar. I think a lot of you will have also seen the recent May geomagnetic storm. Hopefully some of you were lucky enough to be in places to see the aurora. But what was really interesting about this is we saw this large active region on the sun-facing side then rotate round and then was visible by solar orbiter, which is where it continued to be very active. And so actually we saw one of the largest flares of solar cycle 25 on the far side. So this was an X12. I actually changed this because there have been some significant flares since. So this flare was not only detected by STIX on May 20th, but also there was a resulting CME that was detected by MAG as well. And I know there was also some initial observations from Aditya L1 as well of this region. So this CME hit many things out in the heliosphere, not just Parker Solar Probe, Bepi Colombo, but also Mars. And so there was actually a series of CMEs that drove very strong aurora that you can see in the UV by the MAVEN orbiter. But also there was an energetic particle event associated with it. And so you can see it detected by the EPD onboard solar orbiter, but also you can see if you look at the Curiosity Mars rover images here, you can see the specks, the snowstorm effect that you'd expect to see, say, on like the LASCO SOHO coronagraph. So the particle event actually hit Mars too. And so if an astronaut was standing next to the Mars Curiosity rover, it would have received about 30 chest X-rays equivalent of radiation. And so this is currently quite a ongoing area of interest because we need to, particularly if we want to send humans to the moon and Mars, then we need to know about the radiation impacts of these energetic particle events. And that's something that we are looking at with an EC team that has just been awarded. And so to summarise, I hope I've highlighted the importance of multi-spacecraft observations, not just with Solar Orbiter, but also with Parker Solar Probe and other spacecraft in the heliosphere. You can see there's a lot of ongoing analysis, and there's going to be future alignments. What's coming up next? Well, Solar Orbiter's eventually, well, it's actually quite close now. He's going to start observing the poles as the orbit starts to change. And then we'll have the final few PSP counters from December 2024. And then, of course, we've got some upcoming missions, such as the L5 Vigil. There's a Korean L4 mission that's just been announced. And then also, will we eventually have this 4Pi constellation? Because hopefully, as you see from this, it is important to be able to see the many different sides of the sun in order to help predicting different types of space weather. Thank you.
Very nice talk. Questions, comments, please?
Yeah, nice talk, Steph. Those observations from Curiosity, that was the RAD instrument that measured the energetic particles. You should show the plot from that. The other question I had, when you were showing the longitude and latitude of Solar Orbiter and Parker Solar Probe, the timing of that, was that aligned in timing? Because you could have longitude and latitude, you know, you could compare those, but was the timing exact? So they were both at the same latitude at the same time they were at closest at similar longitude?
So from my understanding, that it was still a few days separate. So for example, the fast wind from one of the coronal holes would have been maybe like 5 days different. So I guess it was surprising that we still saw some of the same characteristics in the solar wind measured by both of the spacecraft. But I think we need to, that was just one case. So I think we need to, now that we've had more encounters, we need to start analysing the data to try and compare multiple cases to see if this is indeed the case.
We can have another short question.
So I have a question about the switchback. So one of the alternatives is they could be locally produced in the solar wind, but you know, if there's a shear flow, but in that case, you would expect some vortices associated with them. Do you see any evidence of helical or vortice kind of flows wherever you find switchbacks, or that's not observed?
Do you mean on the sun or?
No, locally.
Locally. I'm not sure. We're currently looking into some of the switchbacks that we saw during the slow solar wind soup in detail. You do see some instabilities there, but I'm not sure about the vortices. We're actually looking at one particular switchback that's very long in duration. But it's ongoing. It's taking time. It's ongoing work.
Sorry, the right light is on. Sorry. Let's move on to the second invited talk. It's about the ASOS mission and the space and ground-based synergies with space and ground-based assets from Bailey. Let's welcome.
Good morning, everyone. My name is Bailey, and I'm from Purple Mountain Observatory. And today I will be on behalf of the ASOS team to introduce the ASOS mission. And then my presentation will include 4 parts, like the overview, observations, and the joint observations with other instruments from China, and the major scientific results. And the ASOS mission is Chinese first comprehensive solar mission. It was proposed by Dr. Wichingam in 2011 and was officially approved in 2017. It was launched in 2022, and our data was released in 2023. And the scientific objective can be concluded 1M and 2B. 1M means magnetic field, and 2B means two bursts, like flare and semi. There are 3 payloads in the ASOS, including a full disk, a vector magnetograph, and a HADES-3 imager, and a Lima Alpha solar telescope. The main goals is to simultaneously acquire the non-thermal images of solar flares in HADES-3 and initiations of semis in Lima Alpha waveband to understand the relation between flare and semis, and to simultaneously observe the magnetic field, the energy build up, and the release of solar flares, and the formation of semis to understand the causality among them, and to record the response of the solar atmosphere eruption, to understand the mechanisms of energy release and transport, and also to provide clues for forecasting space weather. And the ASOS orbit type is sun asynchronous, and the altitude is at 720 kilometers, and the pointing accuracy is better than 36 arcsecond, and the stability is better than 1.8 arcsecond per second, and the design lifespan is larger than 4 years. It will show some special specifications for 3 payloads. For FNG, the spatial resolution is about 1.04 arcsecond, and the spectral line is iron atom of 532.4 nanometer. And the time resolution is around 2 minutes. For HXI, the energy range is between 10 and 300 kV. The spatial resolution is about 3.1 arcsecond. The time resolution is 0.125 5 seconds in the burst mode, and 4 seconds in the normal mode. And for LST instruments, there are 3 instruments, including a white light, a solar telescope, um, in the visible light of 360 nanometer, and a solar disk imager in the hydrogen Lima alpha line, and also a solar corona imager, which can observe the inner corona in both UV Lima alpha line and also the visible light. The field view of SDI and WST is from solar disk to 1.2 solar radii, and the field view of SDI is from 1.1 to 2.5 solar radii. The cadence can be from several seconds to several minutes based on different modes. Okay. The next section, next part is show some ISO's observations. These figures show the comparison of line of sight magnetogram between the SDO HMI and ISO's FMG. FMG can provide localized longitudinal photosphere magnetic fields. Unfortunately, it lacks the routine observed full disk and the vector magnetic fields. And the figure in the left show an example for the active region in FNG field ground and in the line of sight magnetogram. And the right figures show the example for an M-class flare 14 hours before and half an hour before the eruption. For HXI, it can provide the spectroscopy and the imaging between 10 to 300 keV from the Earth perspective with excellent specifications. The figures show the hard S3 source images for different structures such as flare ribbons, post-flare loops, and some details in loop top and rich details of small flares. We also make a cross calibration between solar orbiter sticks and HSI. This panel shows the light curve observed by stick and HXI. And the middle panel shows the HDR3 images observed by HXI. And the right panel shows the reprojected HDR3 source observed by sticks. And the results show a good match. And the LST can provide a Lima alpha full disk and the inner corona image and observes the inner corona in Lima alpha and the white light line simultaneously. And the figure shows some example like Lima alpha prominence, Lima alpha semi, Lima alpha wave, Lima alpha flare, and also filaments on the solar disk and the white light flare. Unfortunately, the spatial resolution of full disk images is not as expected. What's more, the SCI Oh, okay. And he shows some eruption examples in the movies. This is the white light flare and the eruption of the filaments and also the flare ribbon and also the eruptive semi and the prominence observed by SIWL and UV simultaneously, and also other semi events and prominence. And SCI-UV has observed a lot of number of prominence with different morphological structures. The next part is the joint observation with other instruments from China. There are a series of S-class flares occurred in May this year, and so we organized the joint observations of space and ground instruments from China to observe this series flares. An extremely complex magnetic field configuration and photospheric evolution has been observed. The left movie was observed by ISO's FNG, and the right movies was observed by MVST, located at Wuxian Lake in China. And the top movies show the active region evolution on the solar disk for about 2 weeks. The first movie was observed by WST in white light line, and the second was observed by Chase, another Chinese satellite, in H alpha line. And the third one was observed by ISO's SDI in Lima alpha line, and the last one was observed by Chinese Satri in 46.5 nanometer. And the bottom movies showed two eruptive X-class white light flares, and also the corresponding Lima alpha flares. And this figure shows the white light flare spatial and temporal evolution. And the red color indicates the white light flare position obtained by WST running difference images. And here we're also showing the example of the hardest ray images and the spectrum observed by ISO's HXI, and also some radio burst observations from CSO and MUSE in China. Also, a series of semis has been observed by SCIWL, and this series semis also cause the strongest geometric storm in the last 20 years. What's more, we also make joint observations of SI Lima alpha with jet radio heliograph, and the panel shows the prominence evolution in 2 wavebands. The next part is the major scientific results. We studied the decay mechanism of the sunspot in an active region 13229 by using the data of SDO HMI and ISO's FNG. For the magnetic cancellation, the magnetic flux submerged under the photosphere after the positive and the negative poles are cancelled out. And for sunspot decay pattern, we found the submergence of magnetic flux under the photosphere. can cause a rapid flow of surrounding material, creating vortices and accelerating the decay of sunspots. And we also study the QPP oscillation and Hades source motion for an M-class flare occurred on 2025. And the top panel shows the HXI light curve. And this panel shows the Hades source motion. And the right figures show the fitted energy spectrum. And this study shows the clearest sliding process of an Hades source motion on a flare belt. And the origin of this QPP oscillation in this flare is from the sliding magnetic recognition modulated by the magnetic field. And this study promotes a deeper understanding of the mechanisms of energy release from solar eruptions. And also the first 3D diagnosis of Hades sources has been made by combining the sticks and HXI. And the top panel shows the Hades source evolution in the sticks, and the bottom shows in HXI. And the separation angle between these two instruments is around 31.5 degree, and this here shows the evolution of the reconstructed Hades source. And also we has analyzed more than 200 flares above M1 classes and has identified about 49 white light flares. Through these statistic studies, we found that the white light flares are not rare, and the occurrence ratio is around 24%. And this ratio can be higher in the solar maximum year. And this study can provide an important reference for stellar flare studies. And also we studied two cases of white light flare in X classes, and by combining the WST and the chase observations. And the two case studies found that the Balmer continued radiation in the white light flare can not only come from the flare ribbon, but also from a cooling flare loop. And this study can provide critical constraints for modeling flare energy transport and deposition. We also studied multi-layered wave features formed by tilt eruptions. These Lambda alpha waves were observed for the first time by ISO's SDI, and the study of the Lambda alpha, H alpha, and UV waves reveals that the tilt bursts play key roles in the formation of low-layer waves. And also observations and radiative transfer calculations found that the spatial position of Lambda alpha waves is closer to the H alpha waves. And also this EUV wave show a splitting phenomenon. And the fast wave have different propagation speed along and different propagation direction, such as the speed, the wave speed of whose propagation direction perpendicular to the magnetic field is larger than that parallel to the magnetic field. And this movie shows the synthetic EUV images observed based on the MHD simulations. We also make joint analysis of an eruptive prominence with solar orbit matrix. The top movies show the evolution of the prominence in the SDI and SIUV, and the bottom panel shows the evolution in the matrix UV and Y light lines, and the average unprojected velocity is about 480 kilometers per second. And by combining the Y light and the UV observations, and also assuming optical same condition, the temperatures and the densities can be derived. For this event, we found that the thermal energy is almost a constant, and the dashed line indicates the energy obtained by assuming adiabatic expansion. So for this event, additional heating is required. And in the future, we can make more analysis with such PSP, aditya, and so on. And we have submitted and published about 31 papers in the solar physics special issue and 15 papers in other journals. And the final is our data and software website. You can access our data through these links. And if you have any problems, you also can write emails to our team members. And also we have a guest investigator program which can support up to 12 researchers to stay 2 to 3 months in the Purple Mountain Observatory, and the inviters can perform independent or cooperated studies based on or related to the ISO's data. I will stop here. Thank you.
Thank you very much. And
Yeah, great talk. Really nice data. Did you have any observations from this recent May solar particle events and CMEs that
yes,
Steph talked about a little bit? Did you show that?
Yeah, I showed. Hey, where is my?
Yeah.
Yeah.
What's the latency for data access? How long does it take to have?
It's too slow. Sorry.
Yeah, right. There you go. Yep.
This one?
That was last year.
Yes, but it's a little bit slow. Sorry.
Okay.
Yeah.
What is the delay between the time the observations are taken and it's available to the public?
About 1 day, or the first one is
Okay. Oh, that's great. Okay.
yes.
from a few hours, it depends on the telemetry, from a few hours to like more than 10 hours. More questions? It seems not. Okay.
Just congratulations to the Chinese Space Agency. Good job.
Thank you very much. So let's move on to the last invited talk in the morning session by Kasi Sankara Subramanian about the synergy and the potential. Synergy and the potential signs from coordinated observations with Aditya L1 and other observatories.
Okay, thank you.
Okay, that's welcome.
Thank you. And thanks for the organizers to give me an opportunity to present Aditya L1. And as you all know, Aditya was launched sometime in September 2023 from our Indian launch pad. And the L1 insertion happened sometime in January 6, 2024. And July 2nd, 2024, we completed one full orbit in the L1. The L1 orbit time is about 178 days. So I'll briefly mention the individual instruments capability. And there are a few observations which is already planned and executed with other space missions I'll just touch upon, and also tell you the potential of this being used for future coordinated observations. So as you all know, Aditya sits at L1, and it has 7 payloads. 4 of them are remote sensing, and 3 of them are in situ. Some of it is planned. And the remote sensing payload look at the dynamical events on the sun, like CMEs and flares. And the in situ instruments will look at the particles and magnetic fields at the L1 point, which is in the sun-earth line. So you get a kind of an information about 45 minutes to, more than 45 minutes of information would be available for you to, for the particles to reach the Earth place of it. Yeah. Okay, the primary science goals, it's mostly for the coronal studies. And so to look at these large and small scale structures in the corona. And it also has close to the sun, like what the Chinese people told us, from 1.05 onwards, the coronal signatures, which is available. And it also has 1 spectropolarimetric channels to look at the coronal magnetic topology and active region magnetic fields. And it also does coronal abundances studies and the FIP variations during solar eruptions, solar flares, using the X-ray spectroscopic instruments. And this will be the first time we'll have a full disk full disk UV images, near UV images, to look at the variabilities in the near UV and its locations on the sun disk. Somehow it's keep on moving. And which also looks at the studies of the prominence eruptions, both for the quiet as well as the active region prominences. And we have the particle instruments, which is multiple particle instruments located at multiple directions. So it gives you directional information of the events which is observed in the L1 point. And of course, it also gives you the origin of suprathermal and energetic particles, which can be used to study the CME-driven or the SCP-driven particles. Here is the locations of the payloads, the VELC, which is the coronagraph, and the suit instruments, which is located on the top deck. And you have this mobile tower type of instruments, which is the Aditya solar wind particle instruments, which looks at the protons as well as the heavier ions. And the hard X-ray imagers, which is very similar to the HXI, but non-imaging one, which is sitting inside this deck, below the top deck of the instrument. And the other instruments, the soft X-rays, which is below the suit instrument, and the PAPA instruments, which measures the electrons and the heavier ions, and the magnetometers, which is currently, right now showed in the stowed configurations, is in the panel which is facing the sun. So I'll just go through capabilities and preliminary observations from it, go by instrument by instrument. This is the SUIT instruments, which is a filter-based imaging instrument. It's about 11 filters, which is listed here. So which covers the photosphere to the chromospheres, as well as you have 3 bands in the continuum, which studies the in the band which gives an important information to the Sun-Earth connections. The radiations in this will affect the ionospheric perturbations in the Earth atmosphere. And here is a first light image, which happened in December 6, 2023. You can see that we could switch on the few of the payloads before the L1 insertions, and it clearly shows the fine structures in the magnesium band. And so you have this active regions, plages, as well as the quiescence mapped in this particular image. SUIT also have multiple bands. So you have full disk images in multiple band in a sequential manner, which you can see it in the next image. This is taking a lot. Okay, so here is 8 band images, which is seen here. Of course, I mean, this is the first light images, not corrected for any flat fielding or anything. So you see this magnesium lines and magnesium lines, as well as the off-band images of the magnesiums, and the 3 white light images, and other filters in this. Okay, so we have been operating these instruments regularly now. Of course, when it goes there, I mean, there are few events which is captured by SUIT instruments. I think a couple of them I have put in these slides, if I'm able to show it in time. Okay, so here is a small eruptions, which you see it in the prominence eruptions in the SUIT. And on the left-hand side images, what you see here is, okay, as it plays, the left-hand side images, I mean, SUIT also has an option of doing a field of a region of interest observations, so that you can do it faster, faster time cadence. And so that is what is shown in the left-hand side images. So you can choose any sizes from somewhere around 500 by 500 pixels to the full disk images in those regions. I don't know whether this will play or not. So this is a movie of a blob which is emitting during this December 31st X-class flare. Somehow the movie is not playing, and hopefully I think Dipankar has a talk in the last session of this. So we'll try to put those movies in his presentations. I'll go back. I will go forward. We have these 2 X-ray instruments. One is in the soft X-rays and another is in the hard X-rays, covering from 1 keV to all the way up to 200 keV. Very similar to the hard X-rays is very similar to the XXI onboard ASO. This soft X-rays, which goes from 1 to 22 keV, has been observing from the from early December until now. It has captured many hundreds of C-class, M-class, and many number of X-class flares with this instrument. So here is an example taken during this February 1st week, comparing with the GOES and the SOLEX instruments of the same band. And you can see that they match quite well. The difference between GOES and SOLEX is that SOLEX does spectroscopic information, so it gives you a much better what you call data on the plasma parameters like temperatures, emission measures, and the other informations. Just want to show you some example of the data which has been analyzed. Hope it runs. So this is also a spectroscopy which has a spectral resolution which is better than 200 eV compared to RESI, which had a spectral resolutions of 1 keV at around 3 to 6 keV band. So we'll have a better spectral resolutions in terms of detecting those lines. Not moving at all. Yeah, so here is an example of the spectra from say 2.3 keV to all the way up to 14 keV for during a flare. And what we have compared is the XSM instrument, which is on board Chandrayaan-2 of our own instrument. The comparisons looks pretty good between the two. And here is the light curve for GOES, XSM, and SOLEX band during this particular event, which happened on 14th December 2023. And we are able to fit the spectra with these iron lines and iron nickel lines, and also a few of the other lines. What you see here is the silicon and calcium lines. And you could derive the temperatures and the FEB biases, and you can clearly see the variation in the bias during the flare events, which is categorically captured in this particular instrument. And you can also clearly see the differences in the temperatures when you have a spectrally resolved instrument, and then using a band ratio techniques to derive the temperatures. So this is much more accurate in terms of temperatures and the FIP bias or the coronal abundances derivation from this particular instrument. We have the hard X-rays, which covers from the almost like 10 keV, and actually we could be able to go down to 8 keV for many of the cases. 10 keV to go all the way up to the 200 keV band using 4 sets of different detectors. Again, these are all sun-as star images. And here is an example of again the 14th event taken from different instruments. You can see the SOLEX light curve and the Helios light curve from the 6 to 30 keV and the high energy 30 to 150 keV. You can always see these the QPPs which is seen during the peak flare phase of the flare time. And I mean, many nice structures, what you see here related to the reconnection physics, which is happening during this particular flare. And you can also see that pre-flares, so you see a very good multiple reconnections, which is going on, which are all slow mode of reconnections, which happens in this particular event, which is captured with the energy band, which is above 6 keV band. Of course, you do see them in the GOES and SOLEX, but the contrast is much better when you go to the higher energy band. So Helios can also fit because it's also have spectral informations. It can also fit the spectra to derive the electron populations, which is driving this particular reconnections. That is also done for this particular flare, and we have this now regularly available for a multitude of flares during this last 6 months of operations. Then going to the in-situ instruments, the aspects, as I said, it has 2 instruments, Swiss solar wind ion spectrometer, and the STEPS, which is suprathermal energetic particle instruments, covering the energy range from 100 to 100 eV to 20 keV using the Swiss instruments, and 20 keV to 5 MeV using these high suprathermal instruments. And they are also mounted at different locations, as you can see in the next figure, to cover different particle directions, which gives you the information about the anisotropy in the particular event. This has also been switched on from the early phase of launch, and this instrument also has caught the Earth's bow shock regions, and there are pretty interesting results which is under publication. So I think once that comes in or those informations will be available. I think this is also not moving that fast. So, okay, so here you can see, so the Swiss instruments, which is mounted on this tower, which this one has a directionality in the ecliptic plane, and this one has a directionality in the outside of the ecliptic plane. So all the way from 0 degree to 360 degree, which collects all the proton events which comes in these directions. And the STEPS instruments has six instruments mounted at different orientations, starting from the solar radial to the intermediate and the Parker spiral, and the Earth directed as well as the north and south ecliptic directed instruments to cover the particles coming in all directions. Here is an example of again December 14th event, which is captured by these both the THA-1 and THA-2 instruments of Swiss, and you can see these events which happen, capturing both the helium as well as the proton. So from these informations we could derive the flux informations, velocity, as well as the electron temperatures from these data. Here is a comparison of Swiss instruments with the wind data, and they do compare pretty well. And you can see that the locations of these two in the heliosphere. So this gives a good advantage of combining these two instruments to look at the particle propagations in the heliosphere. Here is a STEPS instruments comparison with the ACE instrument, and you can clearly see there's almost one-to-one correlations for the event based ones. And of course, since STEPS has a multiple directionality, we'll be able to compare one-to-one with different spacecrafts. Again, the separation of these two instruments are provided in this particular figure. Here is a comparison of the derived parameters, so the proton temperatures as well as the velocities of the protons. They are more or less matching, except for the deviations what you see here. So currently the understanding of these deviations are being addressed both from the point of view of the responses of the instruments as well as from the point of view of the locational difference between the two instruments. Then coming to PAPA, PAPA has the instruments to look at the electron mode, and here is again the event on 14th December 2023. And this is in the electron mode. You can clearly see this enhancement of the electrons when the event hit instruments on somewhere around 15th of December. This also has some directional information. So the directions of these electrons are embedded in this y-axis here, and it gives you a fair amount of the informations of the electrons, which is coming from which directions of from the sun. Here is the SWICAR instruments. PAPA also has two instruments, one for the electron, another for the ions. This is the SWICAR instruments looking at the ions, ion mode operations, and it also has the hydrogen and helium separations in the ion mode, and also the higher energies, higher ions, which is also this is capable of doing it. So here you can see the hydrogen and helium separations for this particular event. The magnetometer, this is a 3-axis flux gate magnetometer. And here is an example after our bias corrections, which happened sometime in January. So this is after the bias corrections. You can see the magnetometer variations during a February event. And you can see the Aditya L1 as well as the Discovery instruments. They go hand in hand. And we get accuracies of better than 0.5 nanotesla currently with this instrument. Of course, one of the biggest instruments which we look forward is the VELC instruments. So far, the really processed images, if you look at it, we could get the good coronal images from the green line channel, which is the 5303 channels, which we are able to process it, and it required a bit more processing to bring the signals out of the scattered component from the instrument. And here is a comparison of the VLC observed image with respect to an SDO image, which happened sometime in March 26, 2024. The other two channels, the data is available, processing is going on. So this requires some more processing because 7892 and 10747, the signals are fainter than the 5303. So it requires a bit more processing for us to bring out these signals. So currently we are in that process. There is a regular observations of going on in all the instruments, and all the other payloads. The data is available and processing is going on. For the VLC, we have a good processing channel for the 5303. Other processing channel is being carried out currently now. Here is a uniqueness of the Aditya L1. All the blue colors are the one which we have which we have obtained already, and the other three, which is marked in white, is under process for us to establish before we release this payload for general observations. Quickly go through the synergy with other observatories. Of course, many things have been covered by the previous talks. I will not go into the details. We have Solar Orbiter, Parker Plus, New Star, though it's not for solar, but it can do solar observations. Of course, we are upcoming C-core instruments on GOES as well as on CIFO L1. So many of this can be used to study the CME propagations and evolution characteristics. So we also looking forward for cross calibrations with Aditya L1 with other instruments on ACE and Wind and Solar Orbiter. And so the joint campaign observations is currently going on. So I'll not go into much details except for a few cases where you can study with the METIS as well as VLC instruments to cover the large energy ranges, and as well as the Lyman alpha and calcium K images from the suit, as well as the Lyman alpha images from the METIS. And of course, the HXA instrument and the STIX, as well as the Aditya L1 Helios instrument, can be put together for directivity studies, which is directivity studies of these electrons, which is an important element. Which is, I think there is a team at ISSI which is already looking into these particular aspects of this mission. Finally, for the in situ instruments, you have multi-scales observations, especially the mesoscales can be studied by combining multi-spacecraft observations for the in situ instruments. So I will just end up with this particular slide where we are looking forward for the future PUNCH missions, as well as the C-core to cover a larger range of scales from Aditya L1, from the solar disk to all the way up to the 30 solar radii, which PUNCH would be able to cover. Thank you. Thanks a lot.
Thank you very much.
Thanks. It was nice overview, Shankar. I was wondering, you didn't mention Hinode and IRIS observatories. So I was wondering if there is any plan for coordinations with Hinode and IRIS.
Okay, so the SOOT and IRIS observations, there were some during this early phase of, I think, April 14th or so. We had IRIS, SOOT, as well as the Phi instrument on Solar Orbiter, which was carried out as such planned. And of course, yeah, we can combine Hinode and IRIS observations, because IRIS gives you a much higher spatial resolutions compared to SOOT, while SOOT gives you a overall larger, full disk images. It's a good point that we can combine them. Yes.
Yeah, because 10 days ago, we had SWG meeting in Hinode meeting in Bozeman, And this point came up, but it seems there was no answer to how to coordinate between Aditya and Hinode IRIS.
Okay, so Hinode we have not done.
Yeah.
Hinode we have not done, but IRIS was carried out sometime in April. I think 8th or 9th of April, there was some observations.
Okay, thank you. Yeah.
More questions.
Thank you, Sanka. Really interesting to see these first results. I was curious about the 5303 line. Actually, we carried out during the eclipse some observations of the polarized linear polarization of the 5303. I wonder, one, if you were observing in April 9th, 8th.
Okay.
And the second question is, how do you remove the K corona background? I mean, what's the bandpass of the filter for the 5303?
Okay, so the 5303 is spectroscopic data.
Okay.
So it's a raster scan of the spectroscope.
So you also see the continuum.
We also see the continuum. So we use the continuum to remove it. I mean, of course, many of the scattering is also corrected using the continuum.
And you have the linear polarization also.
We do have a linear polarization. So so far we have not operated the polarimetric mode yet, because we had this issue of a larger scatter from the instrument. So we were mostly concentrating on getting the intensity images. And I think if I remember correctly, two times we have done this spectropolarimetric observations. And so the data is being looked into it. And for the April eclipse time, we have not run this spectropolarimetric data. And so
what about the, but still, for instance, would be interesting for us to understand the K corona background. So if you just have the intensity, that would be interesting to compare data.
Sure. I mean, for eclipse time, we have not run this VLC payload. We have not run the VLC observations. Of course, other payloads were operating. At that time, I think we had some maintenance observations for both VLC and SOOT. SOOT was in baking mode. We had a few contamination issues on the detectors. We had to do, I think, couple of almost like 2 weeks of baking, which was going on during that particular phase of observations. So unfortunately, we couldn't do both VLC and SOOT, whereas the other instruments carried out the observations during the eclipse period.
Okay, thank you.
We have to stop here. Let's thank all the speakers in the morning. Do you have something to say? Do you have something to say? No? Then enjoy your lunch.
We reconvene at 1:30.
Tom Shad, and I'm a scientist at the U.S. National Solar Observatory, located on the island of Maui. I'd like to extend my thanks. My name is Tom Shad, and I'm a scientist at the U.S. National Solar Observatory, located on the island mountain. I'd like to extend my thanks to the organizing committee for inviting me to give this talk and for trusting me to give it remotely from Hawaii. Today, I'd like to talk about intersecting frontiers for ground and space-based solar missions. In particular, the focus is going to be on the 3 flagship solar missions of the NSF. and good day.
Can you hear me? Ah, there we go. Okay. So welcome back, everyone. So we are starting our session again. So this next talk is by an invited speaker, Tom Chad, from NSO. So I believe in this session, we have 4 talks, 3 are virtual, 1 is recorded, and we have 1 in person. So the next one is from Tom Chad. So this will be the last talk from the synergetic science from ground and space-based assets. So I believe this is a recording. So if you want to go.
Good afternoon to everyone in Cape Town, and good day to everyone online. My name is Tom Shad, and I'm a scientist at the U.S. National Solar Observatory, located on the island of Maui. I'd like to extend my thanks to the organizing committee for inviting me to give this talk and for trusting me to give it remotely from Hawaii. Today, I'd like to talk about intersecting frontiers for ground and space-based solar missions. In particular, the focus is going to be on the 3 flagship solar missions of the NSF, ESA, and NASA, which are the Daniel K. Inouye Solar Telescope, Solar Orbiter, and Parker Solar Probe. As I represent DKIST, I'm planning to emphasize how modern ground-based solar physics is advancing diagnostic methods in critical ways that help address the common questions that motivate all of these 3 missions. It's important to understand that each of these fantastic missions have been decades in the making. Furthermore, each is motivated by a set of independent, yet linked science objectives that are tied to very old and fundamental mysteries of the sun and the heliosphere. The realization of these projects only came about after tireless efforts to prioritize these science objectives, develop the key technologies and methods necessary to succeed, and then fund, plan, build, and execute. It truly is amazing that we have these 3 missions coming together at nearly the same time, with PSP launching in 2018, Solar Orbiter launching in 2020, and Inouye finishing its construction and moving to early operations in 2022. How do we use the vantage point separately and in combination is critical to resolving many problems in solar astronomy. What are these problems? Well, they include at least 2 fundamental questions. First, how is the upper atmosphere heated, including the chromosphere and the corona? Second, how is the solar wind released and accelerated? And what creates the different kinds of wind? These problems have been around for a very long time. Despite sometimes being claimed to solve, these questions really do not yield simple or even single solutions. A very basic problem is that we know the energy dissipation is occurring on length scales in the solar atmosphere that are observationally inaccessible. And so we must address these questions through intermediary and dynamically coupled diagnostic methods. This motivates some of the key scientific objectives common to DKIST, PSP, and Solar Orbiter. So what frontiers do DKIST, PSP, and Solar Orbiter truly advance? Well, much of the aim is to understand energy flow across key and difficult to study boundaries. From the perspective of the lower solar atmosphere, while we still do not have a complete observational knowledge of photosphere magnetoconvection, radiative MHD simulations do capture many of the essential elements, leading us to a high level of insight into the bottom boundary of the heliosphere. Meanwhile, from the heliospheric vantage point of 1AU, both in and out of the ecliptic, we recognize how the sun creates a diversity of wind types, including speed and composition. The issues arise as we try to form the connections between these vantage points. We have many tools at our disposal, including measuring and extrapolating magnetic fields, tracing transient activity, and so forth. However, we know that these methods often have limits. Moving higher into the solar atmosphere, we encounter the problematic interface where the plasma transitions from pressure-dominated to magnetic field-dominated. Here within the chromosphere, there's a zoo of potential processes at work that are very difficult to observationally constrain, especially as the plasma becomes partially ionized. Radiative line diagnostics are formed in non-thermodynamical equilibrium. Magnetic fields are weaker and more difficult to measure, and wave and mass motions occur on very fast timescales. Tracing the energy transport from the photosphere to that upper atmosphere and then its dissipation is consequently very challenging. Moving towards the sun from a 1AU perspective, there are similar challenges. as the solar wind properties are modified in transit from the inner heliosphere, especially as beta here is generally larger than 1, where the field is dragged by the wind. Consequently, co-rotating interacting regions lead to refraction and compression of the plasma. And wave interactions occur during the transit, and the imprints of the accelerating mechanisms that work near the sun get blurred or washed out. So our vantage points really converge or collide in the low to middle corona and are the alpine surface of the solar atmosphere. The frontiers of observational solar physics is to better probe the chromospheric to coronal mass and energy cycle, where the magnetic field is dominant but poorly understood. The frontier of the space-based missions lie in probing the inner heliosphere directly in situ. Together, then, we can hopefully build a unified view of energy transport from the solar interior to the inner heliosphere. So these great observational challenges posed by the lower solar atmosphere led to the development and construction of the U.S. National Science Foundation's Daniel K. Inouye Solar Telescope. The Inouye, or DKIST, is located on the island of Maui, which is consequently about the antipode of Cape Town. It's in the state of Hawaii, in the Pacific Ocean. The telescope is near the summit of Haleakala, located at about 3,000 meters in elevation. At this height, DKIST is most often above the atmospheric conversion layer, as shown in the upper image. It's an excellent site for high-resolution solar physics, as well as chronographic observations of the sun's off-limb structures. This is due to the very dry and low aerosol content of the atmosphere. The skies can be very, very blue, very magnificently blue. Due to these advantages of this site, DKIST was built here with the idea of being 2 telescopes in 1. It's a 4-meter aperture, diffraction limited microscope in the lower atmosphere, capable of high-resolution imaging down to 20-kilometer length scales on the solar surface. Meanwhile, it is also an off-axis internally occulted chronograph that advances forbidden line spectroscopy, polarimetry of the off-limb corona. Using a suite of 5 diverse facility instruments that cooperate, DKIST is furthermore the world's largest spectropolarimeter for the coupled lower solar atmosphere. Now, let's turn to how ground-based telescopes, in particular DKIST, is helping to trace this energy flow from the solar interior into the heliosphere. Well, using MIRAM 3D radiative MHD simulations of the small solar dynamo, the TS Ripple in 2014 estimated that 50% of the magnetic energy distribution in the solar photosphere occurs on length scales inaccessible from meter-class telescopes. Thus, with this previous generations of telescopes, we are essentially blind about half of the energy available to power the of their atmosphere. Meanwhile, approximately 90% may be observable from DKIST at its diffraction limit. Of course, that's only achievable using an integrated system of high-order adaptive optics. Using adaptive optics and multi-wavelength spectral imaging, the visible broadband imager at DKIST observes at the diffraction limit in multiple photospheric and chromospheric channels, with a reconstructed image cadence of approximately 3 seconds. It acquires 4K by 4K images at 30 Hertz, sampling at 11 and 16 milliarc seconds in its blue and red channels. VBI is starting to reveal a number of spatial features at the diffraction limit of DKIST. Here is an impressive VBI blue image acquired in the continuum near 450 nanometers. It shows interacting sunspots whose penumbra are colliding with each other. In this one image, one can resolve dark lanes separating these penumbra, spatially split umbral dot features, as well as fine lane structures within individual penumbral filaments. Another interesting feature is seen in the intergranular lanes towards the right. These streak-like features extend from the lanes and are being referred to as filamentary striations in a project led by Friedrich Woger at NSO. Zooming in on these striations, we see that the structures have widths down to the diffraction limit of about 30 milliarc seconds. It's also the case that they're more easily seen away from disk center, here at a heliocentric angle of about 30 degrees away from disk center. Comparable features identified in MIRAM models show up when synthesizing the radiation through an inclined line of sight. These structures, as shown here, can be related to the fine-scaled structure of the magnetic field distribution within the intergranular lines. This remains work in progress, but already it's clear that DKIS can resolve a greater portion of the magnetic field distribution in the solar photosphere. In addition to high spatial resolution, DKIS large effective aperture and rapid imaging cameras, provides new insights into how the lower atmosphere can inject energy into the upper atmosphere. On this slide, we see again data from DKIS visible broadband imager. Here, a time series on the left shows photospheric G-band images, and the ones on the right show images in the core of the calcium-2 K line, which samples the chromosphere. You're looking at a segment of the quiet zone at a cadence of roughly 6 seconds, where you sample in between these two wavebands. In this work, led by Kathy and Fisher, DKIS captures shock waves propagating horizontally away from G-band bright points, which is clearly shown within the center of the circle in the right-hand images. These images, or rather these events, are most likely the signature of propagating shock waves that lead to localized heating. Furthermore, the bright points driving these events exhibit some vortical twisting behavior, as seen on the left. It's been demonstrated using kobold simulations that twisted magnetic flux tubes can produce such shock waves. This occurs when they push plasma in their vicinity in what Oscar Steiner in 1998 called a snowplow effect. If you take this simulation and you do a spectral synthesis of the calcium-2K lines, at right, what you get is a reproduction that quite convincingly shows the same sort of horizontally propagating fronts driven from these twisted flux tubes. And so this is to show that DKIS is really starting to quantify these small-scale dynamic events in the lower atmosphere, as well as their transport into the upper atmosphere. Although such small-scale dynamics in the lower atmosphere may play a sizable role in the production and eventual acceleration of the solar wind, it remains actually hard to unambiguously quantify the energy injection rates into the solar wind. Using advanced simulations from the Bifrost code, on the left, Finlay et al. In 2022 found evidence that swirling motions in the lower atmosphere may launch torsional alpine waves that lead to wind and maybe even switchback generation. Meanwhile, in addition to these vertical motions, the role of opposite polarity fields has also been evoked as a critical element in magnetic reconnection driven solar wind, as well as active region solar coronal loop heating. These maps in the center of the slide compare line of sight magnetograms from SDO HMI and co-temporal magnetograms from Big Bear Solar Observatory, their NIRIS instrument. It becomes more and more apparent that one must resolve the photospheric magnetic field at much higher resolution to see the mixed polarity quiet sun magnetic field distribution, as the distribution actually might be ripe to spur magnetic reconnection at high rates. Now, that said, it's also the case that this requires very high resolution polarimetry, not only of the photosphere, but as well as the chromosphere and transition region, in order to truly discern the influence of these fields above the photosphere. Connecting the photospheric magnetic field with the chromosphere, however, is difficult. First, we know the non-force-free nature of the photosphere field limits our ability to extrapolate the field. And second, diagnostics of the magnetic field in the upper atmosphere, as will be discussed later today, require advanced methods not only to measure these very weak signals, but also to interpret the signals as they form out of local thermodynamic equilibrium. Gosek et al. In 2021 used the Swedish Solar Telescope and found some evidence that network emerging flux is able to reach the chromosphere. This is shown in these animations at the right, which first show an emerging flux region identifiable in magnesium-1 linear polarization and circular polarization. When you look at the co-temporal diagnostics of calcium-2 8542 formed in the middle to upper chromosphere, you see in the line core signatures of material interacting with this emerging flux down below. Now, one challenge here is that due to the line formation of this non-LTE line, these studies really need to be carried out with sufficient temporal resolution and polarimetric sensitivity to perform full Stokes spectral inversions. In this case, really it was only looking at weak field approximations and simple diagnostics to show this type of behavior. Achieving high signal to noise spectral inversions is really very difficult, if not unreachable, without a large aperture telescope like DKIST. DKIST has multiple spectropolarimeters that probe the magnetic field from the photosphere to the chromosphere and even in the alpha corona. The visible spectropolarimeter, for example, can observe 3 different wavelength channels from 380 to 900 nanometers. João de Silva Santos et al., 2023, published some of the first high sensitivity maps of total linear and circular polarization in the calcium 2 8540 or 854 nanometer line, as shown here in the middle. This shows a map of the line core intensity, the total circular polarization in the line, and also the total linear polarization. Maps like these and high quality spectra are a first step prior to more routine full spectral inversions of these types of diagnostics. This is the ambition of the NSO Community Science Program for Level 2 data products, wherein multiple wavelengths in multiple BISP channels are inverted simultaneously with the desire code from Huijtenbroek. Of course, tracing the transport of that magnetic and convective energy through the lower atmosphere, even with polarimetry, is only part of the problem. Another still more challenging part is connecting that magnetic field with the dynamic motions in the chromosphere to the candidate energy dissipation mechanisms themselves. Investigating, or rather the need to investigate relationships between the radiative kinetic losses and currents, as well as fluid motions, is really one important critical step. Setsu and et al. 2021, for example, reviewed potential heating mechanisms in Plage network as they relate to the properties of the local magnetic field configuration. However, even with a 4-meter aperture telescope like DKIST, the combination of fast timescales on orders of tens of seconds or less, and the need to cover spatial structures simultaneously, as well as the requirements for spectropolarimetric coverage and sensitivity, all of these things motivate the development of very new observational methods, which is a point made by Tetsu in his paper, where he was using one of the prototypes for integral field spectropolarimetry. At DKIST, it is the diffraction-limited near-infrared spectropolarimeter, or rather DLNRS, that's advancing these techniques to advance simultaneous spectral and spectral coverage over 2D fields of view at a rapid cadence. Recently, the DLNRS fiber-based integral field unit was replaced by a cutting-edge, nano-machined image slicer device manufactured by Canon Incorporated. The images at left show the device that include a slicer unit here in the core of the assembly itself, with 112 mirrors with 36 micron widths, which separate the focal plane and re-image it into 4 staggered exit slits that go into the spectrograph. This upgrade has increased the spectral throughput of the instrument dramatically, and it's also greatly enhanced the flat field stability and the polarization accuracy. Here are some example images from the upgraded DLNRS in its 1083 nanometer channel. Here we use field sampling to increase the field of view. Example Stokes spectral images, as well as the profiles are right, demonstrate that this device is now achieving sufficient accuracy to measure very fine-scaled features in the polarization. Here we can see in the 1080 triplet at 1080, or sorry, the helium triplet at 1080 angstroms, scattering polarization signals of the chromosphere itself. Here you can see signals of less than 0.1% showing opposite sign linear polarization, indicative of scattering polarization and the Hanley effect. While there remains calibration work to do, DLNRS will certainly provide new methods for probing magnetic field and probing the magnetic field and the dissipation of it in the lower atmosphere and in the chromosphere. Moving now higher, as we know, the energy injection continues into the lower corona. And that energy is both in the form of authentic waves, as here shown, observed by the IAU GA instrument, as well as currents and available magnetic free energy stored within the low beta plasma. As for the wave field, Michael Hahn and Savin in 2013 did give some evidence based on anode ice measurements of line widths that waves are dissipated in the low corona. However, these observations can be difficult to interpret and calibrate. How to obtain the amount of energy stored and released within the coronal magnetic field itself is challenged by the limits of photospheric magnetic field extrapolation techniques, as well as the general lack of magnetic field measurements in the solar corona. Linear polarized observations of visible and infrared coronal emission lines do provide constraints on the line of sight integrated magnetic field topology. Meanwhile, the propagating waves themselves do offer a means to measure global magnetic fields using seismology, which was demonstrated by Yang et al. In 2020. However, due to line of sight integration, these diagnostics remain difficult to confidently retrieve 3D coronal magnetic fields, especially in the absence of measurements of the field amplitude. Of course, measuring the magnetic field in the corona is important for multiple reasons, including understanding the impulsive release of energy in flares and CMEs. But also, it's important to understand the corona magnetic field for its potential role in the solar wind release and acceleration above active regions. In this animation by Wiper et al. 2022, it is suggested that intermittent interchange reconnection in active regions may produce a curtain propagating and interacting torsional authentic waves that could then develop into switchbacks within the heliosphere. Measuring the coronal magnetic field from the ground is one of the key science objectives for DKIST. DKIST is an off-axis, internally occulted coronagraph that was designed to advance coronal magnetic field measurements using the Zeeman effect. DKIST off-axis, the coronal magnetic field produces a Zeeman effect signal that's very, very weak. It's on the order of 10 to the minus 4 with the line intensity per Gauss at the iron 13 lines near 1 micron. That results in only a few parts per billion of the disk's spectral radiance. It's a very difficult measurement to make chronographically. Previous measurements, however, were demonstrated by Haosheng Lin in 2000 and 2004. DKIST has recently achieved its first maps of magnetic field in corona, or rather the amplitude of the circular polarization, during the Parker Solar Probe Encounter 16 in June of last year. One of the things that's critical to achieving such a measurement is to have a very well cleaned and polished mirror, which is what's shown over here during an operation using CO2 to clean the primary mirror. In June of 2023, DKIST Cryo-NIRSM instrument targeted this active region in the Northeast. Here is a first look at these maps from DKIST and Cryo-NIRSM. DKIST, on this day, observed a field of view of approximately 400 by 200 arc seconds off limb, acquired using 2 sparsely sampled rasters acquired over 3 hours of observing time. Very deep integrations and careful data calibration at the iron 13 line at 1074 nanometers yielded circular polarized signals concentrated within 3 coherent lobes of oppositely signed polarity signal. The circularly polarized signals are up to 25 parts per billion of the disk's center radiance. If we convert this observed circular polarized amplitude into an equivalent value of the magnetic field in units of Gauss, this is between 10 and 30 Gauss for regions between 1 and 1.1 solar radii above the limb. We find this to be larger by some factors of 5 to 10 of what we see through global models when synthesizing the same signals using advanced methods. These results are currently in press, and we defer to the upcoming article for further details. So with that, I've covered photospheric, chromospheric, and coronal aspects of DKIST and how it relates to this question of tracing the energy. While there are many ways one might speak about how ground-based facilities like DKIST and space-based solar missions like Parker Solar Probe and Solar Orbiter can work together to solve these grand open questions. Today, I have emphasized how advancements in the large aperture ground-based solar observatories are pushing to resolve the bulk of the magnetic effective energy transport throughout the lower atmosphere. This is a critical piece to measuring the energy flow through the heliosphere. Continued efforts to unify these missions through separate as well as coordinated observations is essential. It's important to note that DKIST has dedicated time to do this in coordination, and there's already select public data sets in the data archive ready to analyze. It's also important to note that DKIST is at the cutting edge of ground-based instrumentation, and it continues to mature both as a facility and as a suite of instrumentation that advances novel diagnostics. The coronal magnetic field measurements is a particular success to note in this regard. For further information on DKIST, I would point you to the NSO website at www.nso.edu. And furthermore, the DKIST data archive at dkist.data.nso.edu. With that, I'd very much like to thank you and this organizing council once again for providing me this chance to give you an update about DKIST and how it fits into this frontier of solar and space-based astronomy. Thank you.
So I think Tom is online. I'm not sure how we're able to connect. Oh, there we go. Okay, great. So I think we have time for a couple of questions. If anyone has any questions for Tom. Yep, I think you have to go up to the microphone maybe so he can hear you. Here. Is it on? No?
Thank you very much for the talk. Well, first of all, DKIST has wonderful resolution, but a very narrow field of view when you're looking at the photosphere and chromospheric structures. And then when we look at Parker and Solar Orbiter, we're looking at very large scale structures. So there's a real challenge in trying to connect the observations that we see in Orbiter or Parker with DKIST's photospheric or chromospheric observations. So have you given any thought to how we're going to do that? Because it would seem to me that that's the key part in connecting energy, etc., flow from the photosphere right up into, the inner heliosphere.
Oh, Tom, I don't think we can hear you. Are you muted? Oh, I think he needs to be unmuted, maybe? Or is that us?
Hello?
There we go. Yeah, now we can hear you.
Okay. Yes, that was a great question. Of course, this is very much a challenge, not only for DKIST, but all ground-based facilities with smaller fields of view. We have leaned heavily in the past on the predictions from the PSP team for the foot points of the spacecraft upon perihelion. So we do try to trace at least the predicted foot point as best as we can. But those predictions, of course, are limited, and one thing that limits them is just really our fundamental understanding of the connectivity, as well as the extrapolation of the field. So one thing that DKIST is also trying to do is to really develop that coronal magnetic field mapping technique, such that maybe we in the future will have even higher fidelity in the global magnetic field models to trace that connectivity. But of course, it's going to remain a challenge And at some level, we've got to just do what we can, and then try to trace in the data what we can see once we get it down.
Anybody else? Quick question. Okay, great. Thank you, Tom. Okay, so starting us off on session 2 is so magnetic and wind connectivity science from the photosphere to the heliosphere is another invited talk, and I believe this one's virtual as well. Haru Isa is, are you online?
Yes.
Perfect. I believe you can share your screen. Great. Yes, we can see it. Thank you.
No, thank you very much. So my talk is on the numerical modeling to bridge the solar interior and the solar wind. I'm investigating the physical link between the solar interior and the solar wind, which starts from the photosphere to the chromosphere, corona, and into the solar wind, and ultimately into the interplanetary space. So I think my talk is very close to the last talk, but yes, and my method is to use the numerical modeling to achieve this. So the science target in this talk is also energy and mass transport, especially in the low energy plasma range. And especially the formation of the ambient solar atmosphere and the space environment. And of course, the magnetic convection is a very important factor to do this, because it has two important roles. One is to generate the small magnetic structure, which is observed as a mixed polarity magnetic field in the photosphere, based on the small scale dynamo. And also generated magnetic field interacts with the thermal convection and excites various emitted wave modes, which propagates upward and hits the corona and accelerates the solar wind. So it is important to include the thermal convection into the numerical model. I've been developing a numerical code called Ramens to simulate the solar wind. My code solves the compressive MHD equations with the 1D and 3D radiative transfer equations and the realistic equation of state and the stiff field aligned thermal conduction by electrons. And importantly, we use the orthogonal curvilinear coordinates. So we can simulate the solar wind acceleration along the very small portion of the along the magnetic field lines or magnetic flux tube, which is a small portion of the solar atmosphere. And by including the thermal convections, their heating and acceleration is spontaneous, is self-consistently taken into account. Traditionally, we have categorized the heating process or energy injection process into two categories. One is the DC-like or low-frequency heating process, and the other is the AC or high-frequency heating process. And by including the thermal conduction, we can account both. We can take into account both. So no empirical heating term is required in our simulations. But numerically, it was a very relatively tough task, because the density contrast is very large between the solar interior to the solar wind regions, over the 10 to power by 15. And also it crosses the very low Mach number region to the very low beta solar corona to the high Mach number solar wind regions. So we need to treat such regions in a unified single numerical box. Thanks to the recent development of the supercomputers, we can now achieve such simulations. This is, as long as I know, the first solar wind simulation from the upper convection zone. And left panels shows the cut out from the solar wind regions. And the generated solar wind is structured and rather intermittent. And the right top panels shows the time evolution of the solar wind variables, speed, proton density, and radial field. And it shows a high variability in time. And it sometimes shows the polarity reversals, which is called magnetic switchbacks, which is recently actively discussed by the Parker Solar Probe. And in the corona, this is a differential emission measure in 1 megakelvin. And we found many closed loops and the transient brightenings. And these closed loop structures are produced by the mixed polarity magnetic patches in the photosphere, which is caused by the small scale dynamo. And considering the brightness of the corona and the solar wind speed and density, our simulation was reproduces the slow solar wind from the edge of the coronal holes. And we also checked the lower part of the solar atmosphere. Small scale dynamo generates the closed coronal loops. And we found that between the closed loops and open field lines, interchange reconnection seems to be happening. And this panel shows the 3D view and the horizontal slice of the simulations. And we can see that the gas temperature and particle velocity at the height of 20 megameters above the surface. And we found the hot upward outflows in the open field regions, which was produced by the magnetic reconnection. And the right bottom panel shows the time variation of the coronal magnetic energy and pointing flux into the solar wind. And we found that the stronger the small scale dynamo or the coronal magnetic energy becomes, we get stronger solar wind energy. So in this sense, the small scale dynamo is a very important factor in our simulation. And we also checked the energetical role of the interchange reconnection, which is a reconnection between the open and closed magnetic field lines, and long discussed as a driver of the slow solar wind. And it has two important roles. One is to convert the magnetic energy to the thermal or kinetic energy. And the other is to produce a cross-field energy transport. So we checked that energy transport process produced by the interchange reconnection, and this is the result. According to our analysis, we found that about half of the total solar wind energy was supplied by the interchange reconnection. It means that 20% of the energy comes from the transition region or at the bottom of the corona along the field lines, and the 20% of the energy come from the closed coronal loops. And that 40% energy is used to heat the corona and accelerate the solar wind in our simulations. So according to this analysis, traditional two categories, the AC-like and DC-like processes are both important. Both is very important. So we can now get this kind of classifications. When the induction timescale is small or short, the process will be AC-like, and it will become the turbulence-like or wave-like. it is in contrast to the reconnection-like processes in the DC-like process, and which wave-like process occurs when the small-scale dynamo is weak, and such DC-like processes occurs when the reconnection-like small-scale dynamo process is strong. And that small-scale dynamo may control the total energetics in the solar atmosphere and the solar wind like this. And especially the dissipation height is a very important factor for the solar wind speed, because the dissipation height becomes higher than the fast solar wind can be achieved. So in that sense, the wave-like process prefer the fast solar wind, and the reconnection-like process prefers the slow solar wind, which may be at least partially controlled by the small-scale dynamo, in my speculations. So this raises another open questions. Is such a one-dimensional picture is valid and how accurate, and also H-axis is independent or not, and also such distribution is bimodal, and how can we quantify in simulations and observations? So we need to do a lot to do on these topics. So my next topic, what I introduced today is on the relation between the small-scale dynamo and the coronal brightness in the magnetically open field regions. The coronal hole has been known as a representative phenomena in the magnetically open corona, which is dark in EUV and X-rays and typically appears in poles and magnetically unipolar regions. And it has been known as a potential source of the fast solar wind and open magnetic flux in space. And recently, the open flux problem is actively discussed, which is named by the Linka et al. 2017. There are three constraints on the solar open magnetic flux. One is the in-situ observations near the Earth or in other satellites like the Ulysses or Pegasus solar probes, and which assume the uniform angular distribution, which is confirmed by the Ulysses observations. And also the other way is to use the total magnetic flux in the coronal holes, which is shown in the bottom left panels. From the UV image, we can detect the coronal holes, and also using the photospheric magnetic field, we can mask the coronal hole regions, and then we can average the absolute value of the absolute magnetic flux in the coronal holes, and which might be an indicator of our open flux. And using these second techniques, we can estimate the open flux if we assume that the coronal hole is a dominant source of the open flux. And in the third constraints, we can use numerical models like the potential field source surface models. But these models has many parameters, and which is calibrated by assuming that the coronal hole is open field regions. So the assumption 2 is implicitly assumed. So it is important to check these second assumptions. And the open flux problem is that these three constraints is inconsistent, especially the in-situ value is too large, or the photospheric magnetic field is too weak, apparently too weak, by a factor of 2 to 5, depending on studies. So My talk is on the second assumption, the coronal hole as a dominant source of the open flux. To check this, we carried out 3D radiative image simulation of the magnetically open solar corona. The horizontal domain size is 50 times 50 square megameters, which is a small portion of the coronal holes, or the a small size coronal holes. And the top boundary is 200 megameter above the surface. So our numerical domain includes several gas pressure scale heights in the domain. And the top boundary condition is semi-transparent, so we can the flow and alpha waves can freely go out from the domain. So the corona should be darker than the real sun in our simulation. And we have two free parameters in these simulations. One is the open magnetic flux, open vertical magnetic flux, which is conserved by the periodic boundary condition in horizontal directions. And the other is a small-scale dynamo strength, which is controlled by the recirculation from the deep domain or from the bottom boundary condition. And this is the result. The left panel shows the coronal magnetic field, and the right panel shows the AIA 193 intensity. And from left to right, the open magnetic flux becomes larger, and from top to bottom, the dynamo strength becomes larger. We can see that even if the open magnetic flux is same, when the dynamo strength is strong, the corona becomes brighter, as we expect. And we can classify their simulation into two categories: quiet sun and coronal holes, which is determined by the AIA 193 intensity, which is sometimes used to distinguish the coronal hole, to detect the coronal holes in the observations. So, and according to this analysis, we can see that the bright open region can exist, even though the magnetic field is open into space. And maybe we should skip this. And but if we see a more detailed picture, or if we see pixel by pixels, the coronal darkness is still a good indicator of the open magnetic field regions. This red shaded region indicates the magnetically closed regions. And if we compare this red shaded region and the AI 193 intensities, we can see that the closed or open regions tend to be darker than the closed regions. And also we can see a very tiny open region exists in a brighter numerical box. And we checked the performance of the coronal darkness as an indicator of the open regions, pixel by pixels, using the ROC-AUC analysis. And we can see that this coronal darkness is a good indicator of the open field regions. Although it's not perfect, but it's still a good indicator. So maybe the open field tends to be dark, but there will be one hypothesis that many hidden or small coronal holes may exist in the observations, and which supplies the open magnetic flux into space. Our numerical domain is a very tiny region on the sun, which is 50 times 50 square megameters. And within such regions, even smaller unipolar open field region exists. So if such a region exists, if we see from in the inclined angle, the small coronal holes are hidden by the closed loops. And also the interchange reconnection may also hit the open corona, and which cannot be detected by the dark areas. So the large number of the hidden or small coronal holes may exist, and which supplies the open magnetic flux into space, according to our simulations. So next we check the observations and to check this hypothesis. And we analyze the SDO-HMI and AIA synoptic maps and correct the instrumental degradation and limb brightening effects and detect the coronal holes by setting the threshold value in AIA 193 and measure the signed average flux and the area of the coronal hole above specified latitude. And this is our results. And the horizontal axis is our AIA 193 threshold used to detect the coronal holes as an indicator of the open regions. And we use the higher threshold, we can detect, of course, the more coronal holes. And above the when the threshold value exceeds the typical quartz sun intensity, the dependence becomes weaker. So this is consistent with our hypothesis that there might be a contribution of the hidden coronal holes, even in the observations. If the hidden coronal holes exist, the source surface potential field in the source surface in the potential field models can be lower than the typical traditional value 2.5 solar radius. The left panel shows the open field regions versus the coronal holes. In the left rows, left columns, the lower panels indicate the higher source surface, and in the right columns show the in the upper panel shows the higher AIA threshold to detect the coronal holes. And if the higher AIA threshold can be used to detect the coronal holes, we can allow the lower height of the open field regions, a lower height of the source surface, which infers that the open field region on the solar surface is wider than we expect. And if we can allow, but even if we allow this, the open flux problem cannot be fully resolved. The right panel shows that the interplanetary magnetic field estimated from the near density observations under scaled potential field source surface open flux. And the lower source surface is allowed according to our study, but still missing flux exists, and which may be explained from the systematic bias of the magnetic field observation in the photosphere, which has recently reported in the previous in the literatures. So now I am interested in how can such small open flux reach the interplanetary space, because such small region is of course small, but so it is very interesting why such small region can reach the space, which can be observed as in the form of the coronal outflows or the microfilament eruptions or switchbacks. And these small-scale transient may supply open magnetic flux. And the observational quantification is, of course, it is not an easy task, but very important, I think. And such phenomena is very nonlinear and transient in nature because it relates to the interchange reconnection or magnetic reconnections. So the next generation coronal field modeling may needs to be include such physics because the next generation higher resolution observations like the DKIST or solar C or MUSE may require the higher, more accurate magnetic field tracing to connect the solar surface to the in-situ spacecraft. So, yeah, I guess it is important to update the coronal field modeling. And I hope our study will, can contribute to this. So this is the summary of my talk. We are doing a numerical simulation from the convection zone to the solar wind in a single box to investigate the physical link between the magnetic convection and the interplanetary space. Today, I have introduced two topics. One is the energy partition between the coronal heating and solar wind acceleration. And the other is the brightness of the magnetically open corona, which relates to the origin of the coronal holes. And both two studies shows the importance of the small-scale dynamo as one of the key elements for the interplanetary space environment. So that's all for my talk. Thank you for listening.
Thank you, Haruisa. Are there any questions for Haruisa? I think we have a couple of minutes if someone had a question. Yep, I think you have to come up to the microphone. So can you come up to the, yeah, thanks.
Let's talk. In your opinion, how small could this hidden flux be in the chromosphere or in the photosphere and chromosphere?
You mean the heat flux from the chromosphere into the corona?
Yeah, how small it could be in the photosphere and the chromosphere?
Sorry, maybe I cannot hear your voice very clearly.
Hello, can you hear me?
Yes, now okay.
Yeah, in your opinion, I said this. How small could the footprint of this hidden flux in the chromosphere and the photosphere?
Oh, thank you very much. Of course, it depends on the resolution, but according to our if we believe our simulations, we can observe a few millimeter scale coronal holes in our simulations. So at least such scale is will exist. And if we can do our further higher resolution simulations, maybe find smaller scale may contribute, but it depends on the distribution frequency. So maybe we need to quantify how important it is.
So this one megameter is in the corona, as in the corona.
In the base of the corona.
Just in the okay. So okay, thank you.
Thank you very much.
Minute left, so a quick question.
Thank you for your talk. I have a question with regards to the energy partition, which you showed in interchange reconnection. How does that number depends on the resistivity that you have put in your simulations? I mean, is it like a sacrosanct number because the resistivity will change this energy partition significantly?
Yeah, it is an important factor for the numerical simulations. And what we are doing is magnetic hydrodynamic simulations. And we, to achieve a high resolutions, we need to use a numerical resistivity. So it prefers the fast reconnections. So maybe it may overestimate the reconnection speeds. But also if we but the simulation can achieve a very high resolution, then the plasmoid or turbulence-like reconnection may occur, and such fast reconnection can be achieved. So I'm not my answer is that I use a numerical resistivity, and it prefers.
Sorry. These are ideal simulations. No, you do not put an eta term in your calculations, in your induction equation at all.
Yeah, thank you very much.
Thank you. Thank you.
Thank you. So let's thank our speaker one more time. So next up, next for the session 2 is Javier. So Javier will have, so you'll have 15 minutes. And I didn't mention this before because we didn't have anyone in person, but you have the green, yellow, and red there.
Which one to push? This one?
That's a good question.
I suppose it's the green one. No?
You can try.
Okay, thank you very much.
So the yellow one you have 5 minutes.
Well, thank you. And the main driver of the solar activity is the magnetic field. However, we have remained practically blind to the magnetic field in key layers of the atmosphere, in the upper chromosphere, in the transition region, and the corona. So what do we have to do to reach this goal? The first thing is through theoretical investigations to find observable quantities of the solar radiation that are sensitive to the magnetic field in the upper atmosphere. Then if we are successful, then we have to develop the telescopes and instruments to measure the observables. And finally, of course, we have to develop and apply plasma diagnostic techniques to extract the magnetic field from the observations. And the magnetic field information is encoded in the polarization of the solar spectrum. And let me consider now this spectral region of the magnesium H and K lines of ionized magnesium. The core of these lines encode information on the upper chromosphere, very near the base of the corona. And in the spectral region, we have also chromospheric and photospheric lines. The modeling of these spectral lines, strong resonance lines, is not easy. We have been working with this for the last 15 years. And now we have a fairly good knowledge of the physics going on here. We have to take into account the so-called partial frequency distribution, correlation effects between the incoming and outgoing photons in scattering events. We have to take into account quantum mechanical interference between the sublevels pertaining to the 2 upper levels of the K and H lines. And of course, we have to take into account the magnetic fields, taking into account the joint action of Zeeman effect, scattering processes, and the Hanle effect. I am going to consider now the results of radiation transfer calculations in models of the solar atmosphere, taking into account all this physics. I will show the intensity, the circular polarization, and the linear polarization. So the intensity, you can see it here, it is basically insensitive to the magnetic field. We will have to go to very strong fields to see any changes here. The circular polarization in these spectral lines is dominated by the Zeeman effect. Of course, if there is no magnetic field, you have 0 circular polarization. You have a magnetic field of 10 Gauss, then you have these signals, the K and H lines, and the line number 2 is the subordinate line of magnesium. 20 Gauss, 50 Gauss. The amplitude of the circular polarization scales with the ratio between the Zeeman splitting and the thermal width. There is, of course, also a contribution of the Zeeman effect to the linear polarization, but it scales with the square of this ratio, and it is much more than 1, so there is no signal at all unless you go to very strong fields. Here is a calculation of the linear polarization in the absence of magnetic fields, and you can see that there is a lot of signals of the order of a few %. So the physical origin of this linear polarization calculated without magnetic fields is the so-called scattering of anisotropic radiation. And as I said before, in order to model this, one has to take into account these correlation effects, PRD, and the quantum mechanical interference. As you can see here, what happens if you ignore these effects. Now, let me show the results of some calculations of the magnesium H and K lines and the subordinate lines. This is what I showed before, but concerning now the spectral region of our instrument is the linear polarization as a function of wavelength when there is no magnetic field. If there is a magnetic field now of 10 Gauss, you see this modification. You increase the magnetic field, still more modification. There is sensitivity. We have an observable that is sensitive to the magnetic field, and with 50 Gauss. And the physical origin is, in the core of the lines, you have the Hang effect. And in the wings, you have a new mechanism that it has to do with magneto-optical effects. So basically, this is the summary. The circular polarization is due to the Zeeman effect. The linear is controlled by scattering processes and the Hang and Zeeman effects, and also by the magneto-optical effects in the wings. The Hang effect in the core and the magneto-optical effects in the wings. So these theoretical predictions motivated the development of the CLASP suborbital space experiments in 2015 with Lyman alpha, and in 2019 and 21 with magnesium H and K. I will show now results for magnesium H and K. This is basically the instrument. We have basically two instruments. One is a filter polarimetry, broadband filter polarimetry in Lyman alpha, and a spectropolarimetry across the spectral region of magnesium H and K. I will focus basically on this second instrument because I don't have time. Let me consider first observations of the quiet region close to the limb. You can see here the slit of the spectrograph. And this is the result. As you can see here, in the upper right panel, in quiet regions, we do not detect circular polarization at the sensitivity limit of the instrument, which is 0.1%. The instrument has been developed to be able to detect circular polarization and linear polarization of the order of 0.1%. But however, we do detect in quiet regions the linear polarization, as you can see in the lower panel. Let me make a scan. And here you can see the variation with wavelength of the linear polarization. The black line is observation, and the red one is a calculation in a model without magnetic fields. So the only way we have found to explain the observation is by introducing a magnetic field. In order to extract the information, we had to develop a non-LT inversion code that takes into account all these processes that I have been explaining before. Then the first step is to obtain a model that fits the intensity as a function of wavelength, as you can see here. And now the second step is to continue with inversion and to obtain a model with magnetic field variation with height that fits the linear and the circular polarization. The fact that the circular polarization is 0 is also important, as you can see in the lower panel. It's a constraint. And of course, interestingly, if I switch off in the model obtained from the inversion, if I switch off the magnetic field, I cannot fit the observations. Let me now show you the second target that we observed, an active region plush. Where you can see here the slit was crossing a bright part of the plush and an enhanced network. And here in the right panel, you see the intensity and the circular polarization. So let me make a scan here. You can see here in the lower panel, the circular polarization detection in magnesium H and K, and also in many other lines, in particular these manganese lines, the resonance lines of manganese, which are originated in the middle chromosphere. So if I now apply this inversion code to point C, which is in a bright region of plush, you can see the fit of the intensity in the upper panels on the circular polarization in the lower panel. If I now go to a point corresponding to the enhanced network, this is the fit that we obtain, and the magnetic field for each of these 2 points, for point C, which is in the bright region of the plush, and for the point D in the network, the variation as a function of optical depth is what you can see here in the green and blue curves. The longitudinal component of the magnetic field inferred from the observations. If you apply now this to each point along the slit, you can see here in the vertical axis the longitudinal magnetic field inferred, and on the horizontal each point along the slit. Here we are considering a point in the lower chromosphere. If I now go continuing high, the magnetic field starts to decrease, as you can see here in the middle chromosphere, and in the upper chromosphere the magnetic field is decreasing still further. Okay, you can find information about these works in these 2 papers here, mapping solar magnetic field from the photosphere to the base of the corona. And now in 2021, we did another observation, another launch, but making a scanning. as you can see here in these images. So this is basically the data that we obtained. We have only 5 minutes of observing time with a suborbital sounding rocket. But you can see the detection of all these signals. And the application of our inversion code to each point of the field of view allows us to obtain information not only on the magnetic field, as you can see here, for the low chromosphere, the middle chromosphere, and the upper chromosphere, but also we can obtain information on other physical quantities, like, for example, the temperatures. You can see here the inversion of the temperature. It's obtained from the observations. The temperature increases towards the upper chromosphere, and also on the macroscopic velocities, you can obtain them. So we were able to obtain maps of the physical quantities at various heights in the solar atmosphere. So the inferred magnetic field that comes from these inversions is highly, in the plush, as we knew, is highly structured in the photosphere with strong kilogauss and weak fields. The magnetic field expands rapidly, spreading horizontally in the overlying chromosphere, where it is found to be weaker and with a smoother spatial variations. In the network, the magnetic field changes from about 100 Gauss in the lower chromosphere to less than 10 Gauss in the upper chromosphere. And remarkably, we have found also in this data very high correlation between the magnetic field in the upper chromosphere and the intensity at the center of the magnesium H&K lines. And this supports that the heating of the upper chromosphere in active region plus is of magnetic origin. Well, just to conclude, I think we can say that the CLASP suborbital space experiments have opened a new diagnostic window in solar physics, ultraviolet spectropolarimetry, and what is needed now is a space telescope equipped with this kind of instruments in order to be able to observe routinely this data and to infer the magnetic field in the chromosphere, in the upper chromosphere. So, well, thank you very much, and I will leave you now with this movie of the launch of Class 2, which could be of some interest. So here you can see that once one reaches about 100 kilometers of altitude, then start the pointing system, and we were observing first and the active region plush. This is the launch in 2019. And after about 150 seconds, we moved to the quiet sun limb that I showed before in the talk. You will see it now. Now it is in the quiet sun limb. The pointing was remarkable, fundamental for high precision spectropolarimetry. And then now a parachute comes out, and with a helicopter, one recovers the instrument, and one prays that the data are saved. Thank you very much. From White Sands Missile Range. Yes, from White Sands Missile Range, yes, in the States, United States.
Very nice results, Javier. I have a question for you. In the second flight, the class 2.1,
2.1, yes.
you showed some maps of the magnetic field as a function of height. And
Sí, log tau, yes.
yes, but it seems that you detected opposite polarities with height when going from the lower chromosphere to the
there is a small region where you can see that the magnetic field, instead in a localized region, instead of decreasing, it increases and then decreases again. So this is something which we have now. I think it is also because of the forest short of the line of sight with the bending of this in the class 2.1 data we have a super penumbra, and part of the line of sight is crossing this.
Okay. So you think it's a real thing? Yeah?
Yes, yes. If you could see I can show you the geometry of the field lines, and you can understand that. Yeah.
Thank you.
So the important thing here is that these are proof of concept. With 5 minutes, what we wanted is to demonstrate that these signals that were theoretically predicted can be measured. And in our modest opinion now, the real step forward now will be to put these instruments in space. And there is a mission called CIMEX that is led by the High Altitude Observatory, and we will see what happens. It is in the phase A competition.
Sorry, my question was about the Doppler shifts that you were showing. It looks like red shifts next to blue shifts and a big network of it. I was wondering if those were just little loops associated with the active region.
We cannot say this yet with certainty because these velocities are with respect to the manganese lines. So we have to find the way to make it in a reference absolute. Yeah, but it is the Doppler shift with respect to the manganese lines. But we are working on that.
Okay, so next speaker, our last speaker of this time frame is also online. It is Aishanya. So talking height-dependent variations in temperatures and non-thermal velocities in fan loops. So I believe you can share your screen if you're online. Okay, so we see your screen. I think it's not in presenter mode just yet.
Yeah, can you hear me?
Yes, we can hear you now.
Yeah, just a minute.
Great. I'll come up to the prompter to give you a 3-minute warning, if that's okay.
Yes. Yes. So good afternoon, everyone. I'm Aishwanya Sharma from Department of Physics, Bahana College, Assam, India. And today I'm going to present our work on height-dependent variations in temperatures and non-thermal velocity in fan loops. And this work has been carried out in collaboration with Professor Durgesh Tripathi from IAU GA, Pune, India. So before going into the details of our work, so as we know that many of us know what are fan loops. Fan loops are some of the magnetic plasma structures observed at the edge of active regions, which have temperatures in between 0.6 to 1 million Kelvin. They are one of the very important components of the solar corona, and they act as waveguides for propagation of MHD waves in the solar atmosphere. Another important parameter associated with this study is non-thermal broadening, which is the extra broadening of a line apart from instrumental broadening and thermal broadening. So this is how non-thermal broadening can be obtained. This is the formula. Now, this non-thermal broadening, it's a very important spectroscopic diagnostics, as its accurate measurement can help us to understand the underlying physical mechanisms responsible for the solar coronal heating. For example, non-thermal velocity in the range of 25 to 40 kilometers per second, it can imply acoustic L1 wave flux heating, or non-thermal velocity in the range of hundreds of kilometers per second, it can correspond to nanoflare heating. Therefore, accurate measurement of non-thermal velocity is very important. And for this measurement, the important parameter is this thermal broadening. So how do we measure non-thermal broadening? From the total broadening, we subtract the thermal broadening and instrumental broadening, and we get the non-thermal broadening. And for the measurement of thermal broadening, we need the temperatures. So in most of the cases, generally we consider the peak line formation temperatures. However, it has been found that for the solar structures, the structures may not necessarily be formed at the peak line formation temperatures, and also the temperatures along these structures may change also. Therefore, it is very important to have a proper estimate of temperature and how these temperatures along different solar structures, they vary with height. So in our study, so to estimate the temperatures, we have used one spectroscopic diagnostic temperature diagnostic method, which is known as emission measure, EM loci method. This method gives us the average temperature along the line of sight for a given location in the solar atmosphere. And this method is based on emission measure, EM, which is a function of temperature. And emission measure, it provides us the amount of plasma at a particular temperature in a column along the line of sight. And this is the formula to obtain emission measure, which is the ratio of observed flux. And this is G, which is a function of temperatures and electron density. This is called contribution function. So this contribution function, it contains all the important atomic physics parameters associated with the formation of a spectral line. And D is the distance between the source and the detector. And when we use this EM loci method, at the end, this is how the output looks. So in the output, we get this kind of emission measure curves for different spectral lines. For example, in this plot, Y is the emission measure and X is the temperature in log scale. So whenever these emission measure curves, they cross at a particular point, it means that, suppose, for example, all the curves are crossing at a single point. In that case, we can say that the emission intensity from these various lines corresponds to a particular temperatures. Or we can say the plasma is at that location is isothermal around these temperatures. And for this study, for spectroscopic study, for example, for studying contribution functions, we have used Chianti atomic database in our study. So coming to our study, we are studying off-link coronal fan loops. So the study is carried out by extreme ultraviolet imaging spectrometer, ICE onboard Hinode. So this is our fan loops, and this is our ICE raster. It's shown in silicon 7 to 75.55 angstrom. So to understand, we are considering two loops, L1 and L2. So first we have to consider how temperature is varying along this structure. To calculate the temperature variation, so we are considering some locations marked by these big boxes, A to E for L1 and F to K. And these locations at the bottom, given by these small letters, they correspond to the background regions. For example, when we are taking the intensity from this region A, we will subtract the background intensity corresponding to this small box given by small letter A. And for emission measure study, we need a lot of spectral lines. And in our study, we are using 6 spectral lines: iron 8, iron 9, iron 10, magnesium 6, magnesium 7, silicon 7. It's based on availability and good signal strength. So, and this is how our results, emission measure loci results will look. This is for fan loop 1. So here, and all these different panels show the results for these different locations, A to E for fan loop 1. So for example, for this panel, for these different EM curves, it corresponds to different colors, corresponds to different spectral lines. X-axis is the temperature in log scale, and Y-axis is the emission measure in log scale. So we can see that all these lines, they are not cutting exactly one single point, but they are very near to one part. They are almost closer to one particular point. So to get an estimate of this temperature where they are cutting, so we have at the bottom panel, we have drawn some histograms at a temperature bin of log T 0.1. And we can see that there are peaks. For all the panels, we can see some temperature peaks. So we can say that this location, the plasma at this location is all nearly isothermal around log T 5.8. So similarly, it goes for the other panels. And this is the EM loci results for fan loop 2 for all these different locations after subtracting the background intensity. And so finally, this is this is the temperatures we get for fan loop 1. As we are going away from the fan loop, the temperatures vary from log T 5.8 to almost it remains same 5.85, 5.9. And for fan loop 2, 5.85, almost it goes to 5.9. Or we can say they are almost nearly isothermal around log T 5.85. So now as our main one of our another target was to calculate the non-thermal velocity along those fan loops. Means whatever temperatures we have got now from EM loci method, now these temperatures we are going to use to calculate the thermal broadening, and then we subtract the thermal broadening to calculate the non-thermal broadening and non-thermal velocity. So here this plots, this is for loop 1 and loop 2. We are using silicon 7 line to 75.35 angstrom, as this is an unblended line. And here we can see the red lines. This is the x-axis, this is the loop length, and y-axis is the non-thermal velocity. So we can see how non-thermal velocity, it starts from around 15 kilometer per second. It's slowly varying with distance. It's slowly decreasing with distance for loop 1. And for loop 2, again, this is how, but it's how it's varying. And this black curve, it corresponds to the variation of non-thermal velocity, which is obtained by using peak line formation temperature of silicon 7. But what we notice that these two lines, they lie very near to each other. In fact, the discrepancy is just 1 to 3 kilometers per second. Now, similarly, so this non-thermal velocity measurement we have done for iron 8 line. Iron, again, it depends on silicon 7 and iron 8 lines. We are choosing those lines depending on availability and signal strength. This iron 8 line also for loop 1, this is how the red line, it's decreasing with distance, then increasing. While for loop 2, it's increasing. And most importantly, for the black line, they also lie very close to the red line. Means whether we use the peak line formation temperature to calculate non-thermal velocity, or if we use emission line temperature, emission line loci temperature to obtain non-thermal velocity, the result doesn't vary much. That is something we got from these results. At the same time, we found that for iron 8, if we see along the whole loop length, the non-thermal velocity, it varies from around 11 kilometer to maximum 29 or 30 kilometer per second. And while for silicon 7, this non-thermal velocity, it changes from varies from around 5 to 15 kilometer per second throughout this loop length. So this is something, again, we have found that there is not much similarity in the trend, how they are changing. And for silicon 7 and iron 8, they are a bit different. So maybe we may need some statistical study to confirm this unrelated trend. So finally, to conclude, this is our things. In this study, we have studied the variation of temperature and non-thermal velocity along off-limb coronal fan loops. And the study has been done by ICE on board Hinode. And so we have, by using emission measure loci method, we have measured the temperatures, and we have found that both the loops, they are almost isothermal around log T 5.85. Then we have used those temperatures obtained from emission measure to calculate non-thermal velocity, and we have found that for silicon 7, it lies around 5 to 15 kilometer per second, and for iron 8, it lies around in the range of 11 to 29 kilometer per second. And finally, most importantly, we have found that, yes, even if we use that, most of the studies in the measurement of non-thermal velocity, they use peak line formation temperatures. So in this case, we checked with peak line formation temperatures as well as this emission measure temperatures, but we found that no, there is not much significant difference. It lies almost within 1 to 3 kilometer per second. And with this, I conclude my talk. Thank you.
Thank you. So we have about 3 minutes for questions, if anyone has any questions for the speaker. So maybe I can start us off. So I had a question about the relationship between your non-thermal velocities, but a very constant temperature along the fan loop. at least for one of the loops that you were showing. I'm wondering how you would describe that relationship. You would assume if the non-thermal velocities were going down, there'd be potentially some dissipation that would go into heating.
Sorry, I didn't get off.
So I was just wondering what the relationship would be with the non-thermal velocities going down and the temperature staying essentially constant.
What is the relation between non-thermal velocity?
Right, and then the temperature you were showing initially with your emission measure loci analysis.
Oh, the temperature, because the relation between non-thermal velocity and temperatures, right?
Right, exactly.
Yes. So generally, the non-thermal velocity, or what we calculate it from non-thermal broadening. The spectral lines, they have some broadening. And how do we calculate non-thermal broadening? From the total broadening of the line, from the FWHM of the line, we subtract the thermal broadening and instrumental broadening. And the temperature is used to calculate this actually thermal broadening. So this is how, if the temperature is more, thermal broadening will be more, or non-thermal velocity or broadening will be less. So such kind of relation is there. Mainly, temperature is used to calculate the thermal broadening, and that thermal broadening we are subtracting to calculate the non-thermal broadening. Is it clear? Yeah, one is audible. Is it?
Yes.
Yes.
Yeah, I'll follow up with you at another time. Yeah, if you guys can go to the microphone, I think we have enough time.
Yeah.
Hello. Yeah.
Hello, Divankar. Yeah.
Just to help Ashwarna. So essentially, at this height when the open loop system, you don't expect the long thermal width to reduce. Rather, it actually increases because it depends on the density profile. So there is a density dependence. So the question what I have, Ashwarna, is do you find, because you are particularly looking at off-limb fan loop system, this variation different from, say, adjacent quiet sun behavior or a coronal hole behavior, because that will have an implication in your solar wind acceleration, because often the non-thermal variations with height is actually attributed or used to see where the solar wind is getting accelerated, at what height.
Yes.
Looking at the reasonably sort of, still, less than 1 million Kelvin temperature. So these are the heights where things get accelerated. So do you have some signatures in your analysis?
The variation of non-thermal velocity, or its increase or decrease?
Yep.
No, the trend was not very much clear in our results.
Yeah.
So we can't confirm or conclude much from the results. Yeah.
Has done similar work.
So I think Don has a question for you, but we are officially over time in the poster session. But no, please go ahead. I was just warning
just a quick question.
Yes.
For this non-thermal broadening as a signature of alphane waves or other sort of wave motion, which would also be a reason for observing this non-thermal broadening. Have you investigated that, or have you looked at that as a possible explanation for what you're seeing, either confirming or denying the question?
Sorry, I couldn't get questions.
Okay, well, so wave heating from alphane waves. Alphane waves can also broaden your line profiles.
Yes.
That might be an area to explore.
Yes, very true.
Thank you very much.
Yes, yeah, indeed, yeah.
Very nice talk.
Yeah, thank you.
Great. So I think we're out of time. So let's thank our speaker one more time. Thank you.
Thank you.
So that concludes our session. I think next up is about 30 minutes of poster time, and then back here at 3:30. Thanks.
Okay, hello everyone. Welcome back to session 2 on solar wind connectivity. If I can have your attention, we're going to have the first invited speaker in person. So this is Lucia Abo, and they're going to talk about sources of the slow solar wind and the role of the coronal magnetic field topology.
Okay, good afternoon. I'm Lucia Abbo from INAF, Astrophysical Observatory of Turin. And the outline of this talk will be a brief overview of past and recent results on the topic of the slow solar wind, observation of different instruments of the same feature, the recent observation at high temporal resolution with MATIS, the coronagraph on solar orbiter, and to finish with the perspectives. So this work has been published in 2016, and it was a great effort to summarize very fruitful discussions had during an EC team about the slow solar wind and the magnetic topology. So mainly the sources of the slow wind you can see in this sketch are from the interchange reconnection between field and open field lines at the cusp of the streamers creating blobs from the different expansion factor effect between the streamer and the coronal hole boundary, and also from active region and S-web complex magnetic field configuration. After that, there were many studies connecting the source of the slow wind with the interplanetary medium. Here there are some examples from these studies, and there are also very good reviews on the solar wind topics. I go quickly through this. You can have a look, but there are many interesting points and updating in this topic. But with solar orbiter, we know that there is the very high resolution, spatial resolution, and time resolution, which give another view of the active region, of the details of the corona, the lower corona, the middle corona, and we will see also the extended corona with the MATIS. Yeah. Sorry. And another point is follow the sun from different point of view. This is an example, very nice example, watching the same active region in 1 month long, from April to June of this year, seen by PROBA2, SWAP PROBA2 and Solar Orbiter. You can follow along different solar rotation because different point of view of the spacecraft. And we already seen this recent study published in Nature Astronomy by Yardley et al. 2024. It's about the connectivity of the source of solar wind with the heliosphere, with different instruments. So it's really a good example how to manage this big amount of data that we have in solar physics right now, but we need to connect the source with the heliosphere from the remote sensing instruments and in situ instruments, of course. So I'm talking about the coronagraph MATIS on solar orbiter because with our group, we are involved since the beginning on this. So METIS is an externally occulted coronagraph designed to provide full images of the extended corona. The field of view depends on the position of the solar orbiter, and it provides quasi simultaneously UV and visible light images of the corona in total brightness, polarized brightness, with a spatial resolution and exposure time unique at the moment. And so we can get the density distribution of electron and neutral hydrogen, the solar wind outflow map of neutral hydrogen, and large-scale dynamics during the CMEs. I'm sorry, I just get, okay. Here at the bottom, you can see the field of view of METIS during the perihelion, and the first light of METIS, invisible light, polar brightness, and UV hydrogen Lyman alpha, taken during the by May 2020. And from the first light data, we got the first outflow velocity map of hydrogen, neutral hydrogen, as you can see on the left. There are many assumptions, mainly the electron temperature, because we don't know, we have to assume that the anisotropic degree of the two temperature, parallel and perpendicular to the magnetic field. But we have the diagnostics developed through the Doppler dimming technique. So we can get this outflow velocity maps. And yeah, it's the first time that you can see this continuous map, because previously there was a UVCS with the limited field of view of the slit. And another study about the first light of METIS has been done by Antonucci et al. 2023, and they studied in details the magnetic topology of that period, and mainly the boundary between the streamer and the coronal hole adjacent with the outflow velocity values. Okay, now I'm going to talk about some studies that are ongoing with METIS observations with other instruments. In this case, there were combined METIS and UI observations at the same time. You can see the field of view of the two instruments, and the peculiarity of these observations is that UI was in coronographic mode. So normally he can see the disk, but in this case, and in more other cases later, he can observe also the inner corona, and there is a field of view overlapping between UI and METIS, as you can see, I'm sorry, as you can see in this double circle, okay? And on the right, you can see the magnetic topology of the coronal magnetic field extrapolated by PSI group. So it's during the minimum, almost the minimum phase of the solar activity in 2021. So from the analysis of the emission of the two instruments, METIS and UI, we can obtain information about the physical properties of the streamer in this case. So we have the visible light, polarized light by Thomson scattering, and we can obtain the electron density from there. We have the ultraviolet Lyman alpha light, mainly due to the resonance scattering of chromospheric Lyman alpha, depending on several physical parameters, as you can see here. And from EUI, there is the mainly collisional excitation of iron 910 emission, depending on the square of the electron density and on the electron temperature. So analyzing the emission of METIS and UI at the same time in the overlapping region, so just in that circular region at 4.2 solar radii, we can compare different emission. We can also derive the indication that the iron 10 line is mainly produced by collisional excitation. I don't have time to be into the details. And then from the electron density derived from METIS, we can compute the emission measure map in this way. And from emission measure, we can estimate the counts of the UI, FSI 1074, and we compare the estimation of the counts with the measure counts to derive an estimation of the electron temperature, because here you can see in this plot the estimated counts from FSI, and the horizontal line are the measure counts of FSI, UI, and in the intersection there are double solution, one cold and one hot solution. We have two different measure of electron density. We compare this solution, this estimation of the electron temperature with other studies in the literature, and because it's really important to have an idea of the electron temperature in this region at about 4 solar radii, because there are very few measurements, and you can make extrapolation, but in different way. And the measure of electron temperature is important for the mass flux of the solar wind, and also for the computation of the outflow velocity, as we can see later. Okay, and here it's a summary of the temperature obtained by several studies, previous studies, mainly from UVCS. And in blue color, you can see the electron temperature estimation, and in light blue, it's the estimation in this work. But it's puzzling because then there is the electron temperature derived from PSP, about 3.5 10 to the 5 solar K at 33 solar radii, for example. So it's not really easy to put these measurements all together, and we have to think about that more carefully. From the same data, we can have the results about the velocity of the solar wind. We can produce these maps, but you can be careful when you compute these results, because they depend strongly by the electron temperature, as I mentioned before. Here you can see the difference of the wind speed as a function of the polar angle, 360 degrees, with different assumption of the electron temperature. So it changes a lot. It depends mainly, one of the important parameters is the electron temperature for these diagnostics. So another interesting study, it's a work in progress. It's this one made by Nawin Gampupund. It's investigating solar wind outflows with the solar orbiter and Hinode observations coordinated during a SUP of solar orbiter of coronal hole boundaries SUP. And the context of the observation are this one. In the two rectangular red and blue, you can see the field of view of Hinode ice, and the solar orbiter limb is in white. So there was an angular separation of between the solar orbiter and INODE and the ground observation. And I'm sorry. And this one are the METIS observation during that period last year in April. And sorry, okay. Here there are the results about the observation of AIA and ICE with the upflows, the Doppler shift, and many other parameters. And okay, there is a big difference between the north region and the south region, the red and blue rectangular. One is mainly from the coronal hole, and another one is from an S-web configuration, as we can see here from the magnetic extrapolation. So in the south there is an equatorial coronal hole, and in the north region there is an S-web configuration. So from the METIS PB and the magnetic configuration, we can derive the electron density from METIS observations along the two structures that we see in the extended corona. And when we compute the outflow velocity in the two regions, we see the difference in the speed regime. For the coronal hole, we have, it's an equatorial coronal hole, so it's not polar. We have higher values. There are different assumptions on the electron temperature and on the anisotropy for different colors, but mainly the coronal hole speed are higher than the S-web values in speed that we obtain. This is in progress, but it's really a good example for combining different instruments on different spacecraft. And now the last part is dedicated to the METIS observation at the high temporal and spatial resolution. We are analyzing that because at each perihelion we run this kind of observations, and it's really amazing what we can observe from high cadence observations. So here there is a list of the perihelion 2, 3, and 4 in the last 2 years, but every perihelion we have new observations, of course. The field of view is from 1.7 to 3.5 solar radii in corona. And the type of observations of this kind of observation is in white light. We don't have UV channel in this kind of observations. So we perform total brightness and polar brightness with exposure time of 20 seconds to 60 seconds. And what you can see, for example, here, 2022 along a streamer axis here, different angle position, but following this structure, you can see running difference images, some arcades flowing down, quite here. Then at the end there is also a CME, prominence with the CME, but before that, okay, there are some arcades going down, and there is a continuous outflow, if you see, in all other parts. And if we see in the polar coordinates the same observations. So here is from at the bottom 1.7 solar radii to 3 solar radii, and in with the red line you can see the limits of the streamer. You can see the, sorry, here. You can see flowing down these arcades, and outside there is outflowing. There are some instrumental effects, but we remove all of this during the analysis, and what we get, it's something that it's something new. At this cadence, we never have this data. And for the perihelion of last year in April, we can see here that there is a pseudo streamer on the left and the helmet streamer on the right. On the right panel, you can see the total brightness running difference of these high cadence observations. And you can see, again, there are outflowing towards the external parts and some blobs flowing down, but only in corresponding with the helmet streamer, not the pseudo streamer. So these blobs coming down, they correspond to the helmet streamer. And if we compute the downflows in these cases, we have two different regimes. One between 2 and 3 solar radii, 2.3 and 3 solar radii with higher velocity, and then they slope down at 50 kilometers per second at lower heights. I mean, this before the values are higher, and then they slope down. And okay, we connect this different behavior with the magnetic topology extrapolated by the coronal magnetic field. And okay, and this is my last slide talking about the teamwork in the heliosphere, because there are many spacecraft for solar physics, and in the upcoming years they will be more and more, and we should work like probably it's necessary to work like an EC team with different data coming from different instruments, because I see that it's really difficult to collaborate in only one institute, but the exchange of information about the data and all the problems behind the data, it's probably the only thing to do with the workshop or working group, something like that. And that's all for me. Yeah, so.
Thank you, Lucia. Have we got any questions? Yeah, do you want to go on?
Yeah, very nice talk, Lucia. Question, the calibration for the EUI emission measure compared to the medicine, were there any comments you'd like to make about that? Do you feel?
Okay, so you mean the calibration of the counts?
For determining the emission measure,
the emission
EUI
measure,
and comparing it with another instrument as opposed to two channels of EUI internally.
Yes, so it's a delicate point, and we collaborate with the UI team for that, mainly Federico Scher and Susanna Parenti, and there are some uncertainty in that, but if you consider all the region collapsing, not just a few points, but an angular sector, the signal to noise is quite good to distinguish that one, the signal. But it's a good point.
Yeah, nice talk, Alicia. My point is that you mentioned that the density dependence for the UV and the white light is different. So when we are saying that we are trying to compare a structure, say,
Yeah.
radially out,
Yeah.
so how do you ensure that we are seeing the same thing?
The same thing. Okay, I go back. If I go quickly to the plots. Sorry.
Yeah,
I was
in the
very
past
quick.
also, it has been in the context of CME also, it has been always a problem that whether we see the core as seen in UV or white light as the same object.
Yes, so we average this region, and this region for the streamer, it's not like
really a fine.
okay. So also for Metis, we have an angular sector quite white. And as you can see here, in this plot, there is the counts of the emission as a function of solar radii, and the EUI emission of 175 is this one, okay, this part. And if we extract the square root of the emission, it's quite aligned with the Metis emission. So this is a consideration.
At this height, there is also a concern of the radiative excitation, because you did mention about the collisional part as a dominant for UV, but at these heights, I think for FSI now it has been also confirmed that the radiative excitation is much more important than collisional.
Expected.
So maybe the overlap is quite okay then. Yeah. Okay.
Yeah. Thank you. Yeah.
Any more questions? We've still got some time if anyone has anything. Otherwise, in the meantime, I might ask a question if that's okay. I was wondering how the velocities in the ice data, the Hinode, compare with the outflow velocities that you're seeing in Metis. Is it between like tens of kilometers per second then to more hundreds of kilometers? What's the difference are we seeing from those heights?
We can have a look. Yeah, but the general range is that one. Yeah. So, yeah, there is not a direct connection between this velocity from ice and what we get from UVCS, but we follow we follow the electron density along the field lines that we identified in that region. But yeah, there is not a model from one range of velocity and the other one. Yeah.
Okay, great. If there's no more questions, let's thank Lucia again. And so the next speaker, it's an invited talk by Yami Rivera, and she's going to talk about energization of alphenic slow-speed solar wind.
Yes. Okay. Yes. So first of all, thank you to the organizers for inviting me to give this talk. I'm very excited to be here, my first time in Cape Town. So a slightly different title, comparing the energization of slow and alphanic slow solar winds. So this is a little bit more in line with what I ended up doing since the abstract was submitted. But this is in collaboration with a lot of people, and you'll see why. We tried to really capitalize on the number of observations that we could make to try to bring all of this together from sun through the corona to the heliosphere in various places with Parker Solar Probe and Solar Orbiter. Oh no, what did I do? The green button? Oh. Oh. Oh, I'm sorry. There's a really big green button that I'm just not seeing. But anyways, since we're on here, this slide still, this is a really cool video. This is actually the encounter that I'm going to be talking about is encounter 11. So back in February 2022, very similar to some of the talks that we've already heard about. This is actually what Parker Solar Probe would have observed if there was a camera on board during perihelion. So you could see that big coronal hole right in equator. actually very relevant to a lot of the source region characteristics that we're going to look at. So we talked about this already. I think Stephanie talked about the two missions already, but we have Parker Solar Probe and Solar Orbiter, and this study really couldn't have been done without both of them together, as you'll see. But both in a highly eccentric orbit around the sun, allowing them to get very close to the sun. Parker Solar Probe, of course, so for this study, reaching about 13.5 solar radii during perihelion, getting to about 9 solar radii just below that at the end of the year, at closest approach of the mission, which we're very excited about. So in oftentimes sampling subalfanic wind, right, looking at very young solar wind that is actively being heated and accelerated away from the sun, and Solar Orbiter reaching a perihelion of about the orbit of Venus, and in this case has cameras on board, so taking very, very high resolution images of the sun and spectra, allowing us to really peer into some of the processes that are happening below the resolution that we've never been able to see before, which is very exciting. So together, again, this idea of partnership, like Lucia was talking about, incredibly important to do kind of this next generation of connection science. So very important for the question that we're asking here: how does the solar wind evolve away from the sun? Since 1958, the very seminal paper from Eugene Parker showing if you have this very hot corona, you naturally have this thermal pressure gradient that accelerates your wind out into the heliosphere. Even with this very simple assumption, an isothermal corona, right, spherically symmetric corona, you get this acceleration that happens. And of course, this equation that he was solving was a parametric equation. You have this family of solutions of the solar wind. And down here showing, right, the most physical solution, acceleration out, the supersonic transition of the solar wind. And then also showing them for, right, different coronal temperatures here. So you would get a faster speed for a hotter corona, which makes sense. So since then, we've had a lot of probes around the solar system, including, right, Parker Solar Probe and Solar Orbiter measuring, and then Helios also in the inner heliosphere. And so what we find is that we've kind of have this delineation between the slow and the fast wind that is determined by the asymptotic speed, generally talking about the asymptotic speed near the Earth. Of course, we know generally fast slow wind comes from these coronal holes, open field, while the slow wind comes from these closed field, something that was firmly established with Ulysses, right, during those fast latitudinal scans showing this transition, very sharp transition from fast to slow. Since then, we've characterized the slow wind having this ton of variability that we see. Sometimes its character being very similar to the fast wind, for instance, its composition, temperature, density, and then most recently, a lot of work that has been done by, how do I go back? Raffaele D'Amici is looking at the alphanicity of the slow wind, right? Having the subgrouping of slow wind that is alphanic, very similar to the fast wind, associated with wave energy, and this very non-alphanic slow solar wind. All right. So we also know that once the plasma gets on an open field line, right, once it escapes the corona, that it's not simply just adiabatically expanding away from the sun. When we look at temperature profiles, I'm going to try not to click on the next one and on the actual laser pointer. So this is a temperature. This is a plot showing the temperature as a function of distance from the sun. So this is a plot that was made pre-Parker Solar Probe and Solar Orbiter. You can see this line here shows what the temperature would be like if it was simply adiabatically expanding away from the sun. But this is the data showing that it's very non-adiabatic, meaning that there is some heating associated with in the solar wind after it leaves the hot corona. So you have this coronal heating that's happening very close to the sun, and it continues to be heated as it moves away from the sun. So this is an insert here I put here. This is all Parker Solar Probe data, very close to the sun. We see the same trend. So this is for a polytropic index that would be adiabatic for the temperature, and we see that for different speed solar wind for the proton temperature, and very similarly for the electron temperature, slightly more tenuous relationship to the solar wind, but you can see this non-adiabatic evolution away from the sun, even very close. So what this tells us, again, there's some energy input, right? Some heating that's happening to the solar wind as it leaves the sun. One of the things that I wanted to point out is even when we introduce this non-thermal gradient to the acceleration, it's not able to fully describe the acceleration that we see in the fastest wind that we observe in the in the solar system. So most recent work has found, or at least it's highly inferred, that for the slow solar wind, most of its acceleration can be accounted for by its thermal pressure gradient. So the electrons and the protons kind of doing this, providing this thermal pressure gradient that will likely be able to fully describe its acceleration. We're really excited about a paper that's currently in press with a very similar methodology that I'm going to show here for the slow wind, but for the fastest wind, what's needed is there's this additional energy source that is needed to fully describe its acceleration. And for a long time, that's been, alpha waves have been kind of the thing that people think are likely an important source to the heating acceleration observed, which is what is shown here in this paper. Next slide. Okay, so we talked about alpha waves, so a very specific kind of alpha waves in the form of magnetic switchbacks. So this paper here actually looked at the evolution of a switchback patch from Parker Solar Probe to Solar Orbiter, showing the energy, the kind of energy budget of it, and the translation of the thermal and wave energy into this kinetic energy that we see, and also the gravitational term, showing this acceleration. So what are magnetic switchbacks? So we talked about this a little bit already. A lot of people have been doing, have done studies on magnetic switchbacks since they were first observed during Encounter 1 from Parker. There is, we're sort of converging towards a definition, which I've noted here. So they are large amplitude, sharp alphanic fluctuations with a very constant pitch angle of the electrons. So that means kind of local kinks in the magnetic field as opposed to a change in polarity. And they generally occur, at least from Parker Solar Probe observations, in these coherent patches, right? They're roughly about 5 degrees. And so for this study, so we are very interested in then understanding then the evolution of the slow wind, particularly how the slow and alphanic slow solar wind evolve away from the sun. So what we're doing is looking at the energy budget again, and trying to characterize the important terms that are actually heating and accelerating the slow solar wind. And we're doing this with a conjunction that happened back in February 2022 between Parker and Solar Orbiter. So here on the top plot, we're showing the trajectory of Parker down here very close to the sun, and Solar Orbiter kind of sampling the solar wind that we're interested in the opposite direction in time. And the colored lines that you see here are the flow lines that are ballistically back mapped to the solar surface at 2.5 solar radii. So this is a top-down view of the trajectory. And then below that is showing the latitude versus longitude. So this is the source surface at 2.5 solar radii, showing again the different streams that we're interested in. And we'll talk about some of the properties and how we've identified those streams in a future slide. So here, what I wanted to point out is this particular encounter is very special. So generally speaking, as we kind of hinted at in the first slide, Parker travels very quickly during perihelion, covering a large range of longitudinal, a large longitude across the sun, a lot of different sources associated with just a couple of days. So generally, it's not a surprise to be in a conjunction between a different spacecraft during perihelion. In this case, we had, so the reason why this encounter is so special is because we have coverage of a very large part of the sun, very similar time frame associated with Solar Orbiter, but also they were at very similar latitudes, allowing us to more confidently connect those structures and the properties between them. So we use the back mapping as kind of the zero order connection between them. We can map the two source surfaces and kind of match up the properties together. However, we also looked at different properties to ensure that we were looking at the same streams. So this is, so right left of this slow solar wind period is a current sheet crossing. So everything on this side up to the alphanic slow wind is positive polarity. We looked at the helium abundance between Parker Solar Probe and Solar Orbiter, matching between 1% and 2%. I think Stephanie highlighted the 1% in a study that was done before. We also find 1% to 2%, which is very low for the alphane, for really all of these cases, including the fast. And also, we take a look at the mass and magnetic flux, which is conserved between the different properties, so associated with the individual streams, and also the energy is conserved between them. And so this is really important because this tells us that we're looking at very similar streams. So in terms of the energy budget, it allows us to kind of connect them because we have because energy is conserved. But also, it tells us that because energy is conserved, all the terms that we're associating with the stream, so we've captured here the kinetic, the enthalpy, gravitational, and then this is the alpha wave. So this is the switchback energy associated with at least the slow alphanic stream that I'll mention, that I'll talk about. So these are the energy fluxes. You could see the different contributions of the terms here and are conserved between them. Because they are conserved, then what I was trying to say is the energy that changes between Parker Solar Probe and Solar Orbiter then are directly related to the increase and decrease of the terms associated with these streams, right? So an increase in the kinetic energy would be associated then with the decrease in these other terms, and then vice versa for the different terms. And we can see that. And I also wanted to know some of the terms that we didn't include here because they are quite small. So this is the electron heat flux is roughly 0.1 in this case. Proton heat flux is even smaller. And then the kinetic energy here for the alphas, although we do include them, are very small. So this slide shows the properties of the slow, the fast, and the alphanic slow solar wind that we were looking at between Parker and Solar Orbiter. So the plots are just showing this multi-panel plots. I've tried to keep, so these 4 panels here are the same between Parker Solar Probe and Solar Orbiter. And then in the bottom plot, I'm showing the pitch angle distribution of the electrons here. So there's that current sheet crossing that we were talking about. And then with Solar Orbiter, I have the composition, the heavy ion composition that's measured by Solar Orbiter and not Parker Solar Probe. So here in the magenta is the oxygen 7:6 ratio. So this is a measure of the temperature of the corona, the electron temperature of the corona. And then the iron to oxygen normalized to its photospheric abundance, showing the level of low FIB enhancement that we observed in the different streams. So a lot of different properties here, but what I wanted to point out was how we characterize then the different streams. We looked at the we looked at the cross solicity, which is a character of its alphanicity, and also its asymptotic speed at Solar Orbiter. So at Parker, this is the slow wind stream right after the current sheet crossing here, and then you can see the fast stream is associated with the switchback patch here. There's also switchbacks associated with stuff in between that is really interesting. And alphanic slow solar wind is here. So slow speed but high alphanicity associated with a smaller amplitude switchback patch here. So you can see here the asymptotic speed, or at least the speed at Solar Orbiter, our slow wind stream 380 kilometers per second, our fast 512 kilometers per second, and then the alphanic slow, which is 450 kilometers per second. I also wanted to point out the contribution of the different temperatures. So at Parker Solar Probe, so this is the panel showing the proton temperature and the electron temperature that's in red there. So you can see the growing influence of the electron temperature as you go from this fast wind down to slower and slower wind. Parker Solar Probe, the electron temperature is roughly about 35% of the proton temperature, about half when you get to slow alphanic wind, and then it's 1.25 times the proton temperature there. And so this is really important because these are terms that are going to be important for the thermal pressure gradient and the acceleration associated with the different streams. I also wanted to point out the sources and the associated composition that we measure for these different streams. So we actually just had, we just submitted a paper looking at this more broadly. But in this case, what we find is that the iron to oxygen, this is the normalized iron to oxygen, is between 1 to 3 when we look at the different switchback patches. So between the fast and then the alphanic slow solar wind, showing actually a lower iron to oxygen composition in the alphanic slow compared to the proper fast solar wind, which is really interesting. So that is then related to some of the observations that were taken with SPICE and ICE back at the sun for footpoints associated with these streams. So on the left here is just an FSI image taken around perihelion time, showing the footpoints then of the slow alphanic wind, which is in that red, kind of keeping the theme of the colors, and then the fast wind, which is just adjacent to that. showing the foot points and the sources being kind of the edge of this big coronal hole network at the equator during this time that I was showing in the first, in the title slide. So here you're seeing the outline of a coronal hole. So you can't really see the coronal hole in FSI 174, but we used an AI image to kind of map that, same day image to map the coronal hole network. And then below that, you can see very faintly, this is SPICE and this is ICE. In this case, solar orbiter is very close to the sun-Earth line. This was taken just at the center of the disk from the sun-Earth line perspective. Up here is then a zoom in of SPICE and ICE. So this is the emission of neon 8. And then next to that is a map showing the FIP bias between magnesium and neon. Again, so providing somewhat of a comparison to the observations in situ made with Solar Orbiter, different elements, but we are looking at this is a low FIP to high FIP, low FIP to high FIP between iron to oxygen. So you can make some comparison here, but they're different elements. And so if you remember, our alphanic slow solar wind, which are the foot points here, are associated with a very photospheric iron to oxygen. We find in this case that to be true within the coronal hole itself, which is very compatible. But one of the things you may notice is also that the entire map shows kind of this more structured iron to oxygen, magnesium to neon distribution across that. So the outline of the coronal hole is here, but it's really hard to tell what is what if the outline wasn't there. So I thought that was really interesting, probably worth looking into. And then with Hinode ice here, so we have the emission and then the Doppler shift here, which are fairly weak for this being part of a coronal hole. But the idea here, so we don't have foot points from ice, but the idea is these are both taken on the same day, very similar. They're capturing the coronal hole network that we're seeing. And so the idea with including these remote sensing observations is that we would have some measure showing compatibility between the mapping in the iron to oxygen, the magnesium to neon, some compatibility there, and getting an electron temperature and density with the Hinode ice observations and also composition. Unfortunately, one of the things that I found is that it is incredibly difficult to do that for regions of coronal holes because a lot of the lines are they're not very strong. And so I'm very limited to the number of lines I can use for emission measure loci that we were talking about before. So what we're doing is then trying to compute an electron density and looking at then line ratios for the electron temperature because we don't have enough lines to actually do the full analysis there. But this comes into play, the temperature and the density associated with the modeling that we've done in terms of some of the coronal observations that we can then constrain, making this kind of a compatible across the corona, the source region, the corona, and then throughout the inner heliosphere. So these are some solutions from a model that we've done. So this is Parker solar wind solutions in this case that have been the formalism has been developed in these two papers. The idea is that you would have these, similar to what we talked about before, the 1958 paper from Parker, you would have these solutions in which you would have this isothermal layer, this is pink layer here, associated with a constant temperature. That would then transition into a polytropic solution. And you'd couple those in such a way where the pink would be a description of the evolution through the corona. And then this is our heliospheric evolution. So here we have an opportunity to then constrain this evolution from sun to the inner heliosphere by incorporating all of these measurements together, which is what we've done here. So here is so these two are showing the density profile then of the slow alphanic wind, the slow wind. So we map then, or we fit rather, the solutions to this density profile. And then same with the temperature profile, we have measurements at Parker Solar Probe and Solar Orbiter in both cases. So for the proton temperature case, we have a measurement both at Parker and Solar Orbiter. However, we don't have an electron temperature at Solar Orbiter. So the solutions that you're seeing here, the temperature profiles that you're seeing there are actually coming from the literature. So this is from DeCao 2022, which looked at this ensemble of observations of the electron and proton temperatures and came up with a polytropic index that associated with a particular solar wind stream. And so this is really as good as we can get without a measurement at Solar Orbiter. And so the center column then is the velocity profile, the resulting velocity profile associated with the temperature profile, right? This thermal pressure gradient from the electrons and protons associated with the slow alphanic wind. and the slow wind. And so one of the things that we find is that, just as we suspected, very similar to the fast wind, this is the curve here in the blue, in the dashed blue, is from a contribution of both the proton and electron thermal pressure gradients. And then this red curve here, in both cases, is including the wave pressure gradient associated with measurements taken at the two streams. So incorporating the influence of waves, right, direct through this direct kinetic translation, right? And so what we find is that we can only meet the acceleration of the slow Alfvénic wind when we include the waves in this case. Whereas for the slow wind, we find that, so in this case, there's this magenta version of the line here that actually meets the velocity observed in the slow wind. And the reason for that is because our polytropic index for the electrons are actually a little bit small, a little bit more shallow compared to the observations here from DeKeo 2022. Ultimately, the summary, I've tried to summarize some of the results here, which is showing the influence of these different terms to the heating and acceleration of slower and slower wind in this case. So for the fast wind, the waves are incredibly important, the waves in the proton thermal pressure gradient. That becomes a little bit less important here, but still driven by the protons and the electron and wave contribution. For the slow wind, the waves actually don't contribute a ton to the acceleration, but it's mostly driven by your thermal pressure gradients with the electrons providing even more acceleration. And next slide. There we go. So this is just a summary of the results. So this work, we looked at the radial evolution of slow and slow Alfvénic solar wind between Parker Solar Probe and Solar Orbiter, and use all of these different elements to show the connection between Parker Solar Probe and Solar Orbiter and also to the sun. We of these different streams and try to map them back to the sun, to FSI, SPICE, showing that at least for the case of the fast and the slow Alfvénic wind, they are generally related to coronal hole, the coronal hole at the equator, right at the edge of the coronal hole, which is really interesting. And then modeling results show, as we saw in the previous slide, so we have slow solar wind that is driven by the electron thermal pressure gradient, and of course the protons as well, having very little acceleration coming from the wave pressure gradient, so from the Alfvén waves. Whereas for the slow wind, the Alfvén waves, of course, there is a contribution from the protons and the electrons from the thermal pressure gradient, but you do need the additional energy from the waves to fully describe the heating and acceleration in this case. And I think just 1 minute, I wanted to share one slide, kind of in the spirit of this meeting, trying to think about collaborations, future collaborations with missions that have just coming online. So this is an example, a way in which we could potentially integrate, this type of study with ADICHA, which is already taking both remote sensing and in situ observations of the solar wind. So this I was involved in leading coordinated efforts between these all of these different measurements during the eclipse. So this is showing ground, airborne being ACES here, and space-based observations that we were coordinating during the eclipse back in April over North America. And of course, we have, so during the eclipse, Parker Solar Probe and Solar Orbiter were off to the west limb. And before that, during the trajectories, had just been through perihelion in both cases. So passing over the sun-Earth line, but we're on the west limb during the eclipse. And it was very interesting because this is an opportunity in which ADICHA could be very easily integrated in association to these different measurements. ADICHA taking measurements of the green line of the corona, which is very hard to do from the ground, which is very exciting, and also taking observations of protons and alphas at L1. And so there's an opportunity here, both of them cross the sun-Earth line, having this additional observation of the corona with ADICHA could be very beneficial to then this multi-wavelength analysis that we're aiming to do with this coordinated study. And this is something that we have actually written up. It's a Solar Orbiter Science Nugget. If anyone's interested, also come and talk to me if you want. If you want to learn more about this coordinated study. But we're very excited about it, and it's ongoing work. So, yep, that's it. Thank you.
Any questions?
Very nice overview, Yemi. Can you make a comment or maybe talk to the understanding of the switchbacks of solar probe like that Steph brought out earlier in the day?
So I actually didn't point this out, I think. Go back. So we recently submitted a paper looking at the heavy ion composition of switchbacks, which is really exciting because heavy ions will tell us about sort of if the wind that in which they are embedded is open or closed field or some combination of that. And one of the things that we find, which could be very interesting in terms of its formation process, is that the iron to oxygen, so we're actually using this conjunction. So looking at wind over here and also across the current sheet, looking at the switchback patches with the heavy ions, so iron to oxygen from solar orbiter, and finding that there is not one single iron to oxygen value that you could associate with it. Large scale structure seems to be between 1 and 3, meaning that we're looking at values that come from coronal holes up to maybe quiet sun type low FIP enhanced values. What this tells us then, open and closed field contribution of the wind in which they are embedded. So doesn't really tell you exactly about the formation process because there are a couple of different ones that it would be, you get a low FIB enhancement between 1 and 3, but it does kind of narrow down the idea of where these come from. And also, right, we do have some idea of the related to the FOC points and associated with the switchback that we're looking at. We do have some idea of where they're coming from at the sun. So maybe just to summarize, I would say it really does tell us that these switchbacks are potentially forming in solar wind associated with the edge of this coronal hole, a boundary of coronal hole where open and closed field structures can exist.
Okay,
To summarize.
All right. Thank you.
Thank you, Yemi. So from Ulysses, the solar wind, the fast solar wind is relatively steady, while the slow wind is highly variable. So this variability from both orbiter and probe, can we trace it, whether it is an evolution thing or it is from the source that is coming from the source?
You mean the composition?
No. Variability of the wind itself.
Okay.
Yes.
I guess by variability, I was talking about composition and also temperature and density and things like that. But to me, what that tells you, at least from the composition side, is that you have contributions from these different sources together, right? So if you had something like interchange reconnection, there would be some contribution to both fast-like composition and closed field slow-like composition for the an asymptotic split that we can consider slow, right? So the idea is that you would have some more dynamic creation of the wind associated with it. That's what I think about it, because when you look at the composition, it's very much, it can be very, very similar to the fast wind, and it can be very different. And so we have this, you can have some really extreme values of iron to oxygen, which tells you that they're probably coming more from active regions, because that's where you find the most extreme low FIP enhancement. But I see I'm out of time, so I don't want to go over, but we can talk more.
Yes, very quick. Actually, it's, by the way, very interesting results, especially the one regarding the fast wind, where, there are indications that there is deposition down to 10 solar radii. Actually, just wanted to point out that UVCS on SOHO already saw indication of continuous deposition of energy through the broadening of the minor ions and proton, hydrogen down to already 2 solar radii. Back then, the interpretation was ion cyclotron resonance. There, the papers are still in press regarding Alphen. Do you have any comment on that?
Yeah, so I guess that would be expressed in, so they were looking at the temperature anisotropy, but also the ion temperature, right, of oxygen and magnesium compared to the protons, which is already out of thermodynamic equilibrium in coronal holes just within a solar radii. Yeah, I mean, that's something that you can continue to look at, right, in the inner heliosphere. Solar Orbiter has, so they have the ability to measure heavy ion kinetics, so temperature and velocity as well, so differential streaming and temperature compared to the protons. So that is really interesting, and it's actually something that I'm looking at because
it's interesting that this deposition starts right away.
Exactly, in fast solar wind. Yeah, right.
Great, let's thank Yemi again. And so our next speaker is Piali Chatterjee, who's going to talk about solar wind near coronal streamer structures using 3D MHD simulations in spherical geometry.
Yeah, and that's the light pointer. Many thanks to the organizer for this opportunity and to allow us to present our recent and ongoing work. Basically, the final aim is to study coronal flux rope activation in presence of ambient magnetic field. So these are actually a very simple class of models that we are studying. This is a full MHD model, but the magnetic topology is actually very simple, falls in the class of models known as data-inspired models. And the topology we have is actually basically related to these streamers, the flux ropes present under streamers, which form around these polar crown filaments. Need not be polar, I mean crown filaments. So we have developed this model of CME initiation in spherical geometry, and this follows a lot on these previous work here. And we developed this model further to understand, basically activate the solar wind near a coronal streamer by varying the heating in the solar corona. So this is a parametrized heating. Let me see if, yeah. So we use the pencil code, which is an open source code. So, and this is basically our domain. So we have these arcade-like geometry. And the initial setup is a very simple gravitationally stratified isothermal atmosphere, though the simulation is not isothermal. Let me emphasize that. And the lower boundary, which is essentially located at one solar radii, is actually not the photosphere, but should be treated as the lower corona. So basically the magnetic fields are much lower than what you would expect in the photosphere. So we are not resolving the things in the photosphere and the chromosphere. And it goes only till the lower corona. So the top domain is in 6 solar radii. And we have these additional ingredients. For example, anisotropic heat conduction along field lines, optically thin radiative cooling, there is some volumetric heating, and there is also these semi-relativistic Boris correction. Okay, so these are the equations which, I need not say, but in the pencil code, we actually don't solve for the magnetic field itself. We solve for the vector potential so that we don't have to do what is known as divergence cleaning. And then we have the heat equation, the conduction, which is basically solved using a telegraphic equation. And this is the heating, which is parametrized, so it is not self-consistent, but there are these parameters we can vary and change the heating in the solar corona. Because of course we are not resolving the waves and reconnection and things like that. That's not the point of this work. So what we do is we have the lower coronal boundary, and the initial field has this parallel arcade structure. And from below the domain, we essentially push a twisted torus. So for example, you can understand how twisted the torus is by following this black field line. So this particular torus has 5 winds of one field line along its circumference, for example. And this torus is actually pushed really, really slowly, quasi-statically. That is the term used.
into the domain so that, the rise velocity is much, much less than the Alfvén velocity at the lower boundary. So that, the magnetic field in the corona reacts much faster to how fast I'm changing the conditions at the lower boundary. So that's basically the idea. So this is pushed by applying a electromotive force as the lower boundary to push this twisted torus quasi-statically. And this is what happens when we do that. So there's the flux rope evolves. And so basically this time indicates the time after the start of the simulation. So we really slowly, we push this torus inside and there is one eruption that happens. And then there is a next eruption that happens. So there are a series of two homologous eruptions. So I hope this movie will run again. It's the same movie of the last picture that you saw. So there's this slow build-up and abrupt release of the magnetic energy. This of course is not new. I mean, Yu Hong simulations already show this. And okay, so then this is some more properties of this simulations. There are two CMEs. And they erupt we think they erupt due to different instabilities. So you see the kinetic energy in red and the magnetic energy in blue. So you see these two step down functions here. So this is the first eruption, this is the second one. And what we find is the flux rope at the first CME eruption actually erupts due to the torus instability rather than the helical kink instability, because the number of windings of the field line between the line tied ends is much less than the critical number of winds as predicted by Eric Priest's paper. But the second eruption, during the second eruption, it's not torus, it's also torus unstable, and is also unstable to the kink instability, because the critical winding number happens to be around 1.25. So I think in the case of the second flux rope, we have both instabilities acting in tandem, whereas in case of the first flux rope, we only have the torus instability. So now what do we do further with it? So of course, there is a loss of equilibrium. So we are dealing with a model in which the flux rope is rising due to a slow tether cutting reconnection up to a critical height and then erupting. But then once there is a loss of equilibrium, what determines the velocity of the CME is, one of the important questions. Of course, there is this magnetic energy release, the release of free magnetic energy, which is available for conversion to kinetic energy. But what exactly determines this velocity is one of the questions. So what we do is, sorry, let me go back here. Yeah. So what we do here is try to estimate the reconnection flux that is available when the flux rope is going through this eruption process. So what we do is we trace this, we basically plot this current sheet first, and then we plot field lines passing through the current sheet, and we look at where those field lines are tethered and what is the temperature in that region. So basically we look at these what are known as flaring ribbons, and what is the flux passing through these flaring ribbons. That is the measure of the reconnection flux. So that's actually much simpler to do from a simulation than from observations. But this is again also inspired by what other authors have also done using observations. So basically they do this area of flaring ribbons and they estimate what is the reconnection flux. So that's what we have done. So these are the reconnection flux in the case of two CME eruptions. And the red color indicates slightly before the eruption, initiation of the eruption. And the blue one is slightly afterwards. So you see that the reconnection flux increases and then tends to stabilize and then decrease in both the cases. And then what we do is we also estimate this velocity, the flux rope rise velocity in both cases by, just plotting a simple height time plot in both cases, where so this is a density plot essentially, and the darker region corresponds to the core of the flux rope essentially. So we are basically looking at how the flux rope is rising. So if you take the slope of this curve, you will get the velocity of the rise of the flux rope. And here is again the velocity. So the convention is the same. Red is before and blue is after. And once we have the velocity as well as the reconnection flux, of course, then we can correlate them. So these are the results: reconnection flux versus the velocity in both cases, before and after, by this red and white. The red and blue. And we do get a pretty good correlation between the reconnection flux and the velocity, both slightly before and after the initiation of the CME. Then we would like to actually see if such a thing is seen in observations as well. And people have seen it, but then we found a particular event which is special. Because this event was on disk from SDO, so which basically means that we can easily estimate the reconnection flux, whereas it was a limb event as far as the stereo A observations go, so that we can estimate the velocity of the CME. So there are not many events like this, but there are a few, and we basically study one of them. And this is how the flaring ribbon area is calculated. So this is basically looking at this AIA 1600, which is looking at this chromosphere transition region temperature. So this is the flaring ribbon area which we identify, and this is overplotted on HMI magnetogram. And then we basically calculate the flux through it, the unsigned flux, and just divide it by half. So that's how we can estimate the reconnection flux. And that is what has been done, for example, here. And similarly, this is the result from the stereo. So this is coming from SDO, whereas this is coming from stereo. And we do see that there is also a very good correlation between the reconnection flux and the speed for this particular event. So we have only done this for this particular event, but there are other papers which have done it for different events, but the difference is that they have not done a time evolution. So this is one of the cases where we did a time evolution for one particular event. So now, after this result, what we do is we try to make the simulation more complex by activating the solar wind. So we follow this recipe given in Yu Hong's paper. So what we do is we decrease the pressure by half at the top boundary, and we allow mass flux through the lower boundary to activate a solar wind. Now, even when we don't do that, suppose we don't do this, what happens is, because of the heating, there is still some solar wind, but that solar wind speed is very, very less than what you would expect. So we start this solar wind here by, if you use this recipe, then we get a solar wind. And our next, and then again, we introduce this flux, the flux rope here through this, in this particular way, in the solar wind, in the model with the solar wind, and we again have an eruption like this. And we study that in this eruption also, the activation, the flux rope activation occurs because of the kink instability, the helical kink instability. So this is basically our summary when we continuously immerse this flux rope into the domain quasi-statically, and we can use this model to study flux rope activation. And in the first result, we see that in both CME eruptions, the reconnection flux seems to have a strong correlation with the velocity of the flux rope. And in a similar setup, we switch on this solar wind, and then we can use this model further to do this prominence eruption studies. So I thank you for your attention. And before I leave, I would like to draw your attention to this conference, Sun, Space Weather and Solar Stellar Connection, that we are going to have in Kodaikanal Solar Observatory in January, because we are celebrating the 125th year of the Kodaikanal Solar Observatory. So I invite you to come to India. Thank you.
Any questions? Quick question. I've got one for you. Have you tried calculating so you do this reconnected flux with the flare ribbons. Have you tried it with the coronal dimmings? Because obviously there's different methods that you can do to calculate the reconnected flux.
So there are actually this post-eruption arcade method by Gopal Swami, and there is also this dimming method, but we have not used, but as I understand that they both give very similar results. Probably this post-eruption arcade gives a slightly higher reconnection flux, but we still think the proportionality is strong, and maybe it is driving, maybe there is some causal connection.
Thank you. Let's thank the speaker again. Okay, so our final speaker is Sanjay talking about estimation of projection effects in near-limb solar magnetic flux measurements, advantage of multi-viewpoint observations, and this is going to be a virtual talk.
Hi, can you hear me?
Yeah, we can't see you yet.
Yeah, can I share my screen? Because it says, okay, now it's allowing me.
We can see you now.
Right, okay. Can you see the screen?
Yep, you can go ahead.
Great, okay. Yeah, I'd like to thank the organizers for giving this opportunity. And this is a work that I would like to present on behalf of myself and my collaborator, Han. We are from NSO Boulder. We're talking about the projection effects on the magnetic flux measurements, especially away from the disk center, and how multi-viewpoint observations are key to do such measurements. So, it's been more than 100 years and since the discovery of magnetism by Hale, and then on the solar, in the sunspots, and then we have systematically made these measurements for many years now, but still the solar activity remains poorly understood. The butterfly diagram here shows how the 22-year magnetic cycle progresses. And but still, making a prediction of how strong the next sunspot cycle would be is a challenge. Babcock and Leighton, they gave a phenomenological model of how the polar field kind of acts as a seed field for the upcoming cycle. And also that's something that people currently use for predicting the strength of the following cycle. So it's really important to measure them accurately to really understand and make accurate predictions. But also the polar field distribution dominates the global structure. As you can see, it's in these model fields, most of the time during activity cycle, the heliospheric field is dominated by the structure of the polar field distribution. And it's seen in these coronal hole maps. And so basically, this is the main source of interplanetary magnetic field via these regions. And it's very important to measure these in order to understand how the whole interplanetary magnetic field behaves during the cycle. Then there is this open flux problem. In recent years, people have emphasized this. What is open flux problem is that basically at 1 AU, when you measure the interplanetary magnetic flux from in situ observatories, it doesn't match with the flux that you calculate from the global synoptic maps of the magnetic flux using models. So this paper by Linker et al., and they have shown that it's a factor of 2 to 4 smaller that the models give. Both MHD models, PFSS models have been used, and both cannot explain the deficit. So the kind of conclusion that they draw was that either the synoptic maps are not properly measuring the flux, or somehow we're missing where the open magnetic flux is rooted. Maybe not all is rooted in the coronal holes. That's the assumption. So better algorithms have been, I mean, there's so much work that has followed after that paper. And so they're trying to find a resolution to this problem. And then there's a coronal hole have been detected using better algorithms, and they still find open flux. And there people have tried to change some parameters in the models, like varying the source surface radius. And again, there are some inconsistencies with that. And then people have also tried to go fundamentally into the data of the magnetic flux that is used in these studies from Mount Wilson, and Wang et al. Studied the Zeeman saturation problem in the magnetograms, and they tried to explain it in terms of that effect. Wang and Shili, they showed ICME, maybe their contribution can explain this, but however, again, that's model dependent to some extent. And then again, so I mean, there are various ways people have tried to explain this, but the summary is that people have tried to explain this in different ways, and so we don't know which one is the best or the correct way to explain this. So too many smoking guns at the same time, so we don't know which one is the real one. So I would like to emphasize the projection effects. So I think there is a fundamental limitation to when you are viewing at the polar regions from an oblique view, like from the ecliptic plane, there is some fundamental limitations. And so one is, of course, the foreshortening effect. So as you go towards the limb, you have, even with higher resolution telescopes, you only sample much larger areas on the sun. So your averaging effect is canceling a lot of flux. But apart from that, I think, so this is on the top panel here on the right, you see a vertical cut in an MHD simulation sampling the flux tubes in intergranular lanes. And the red line shows the optical depth unity and kind of the surface that we see. And so while you want to measure these strong fluxes rooted in these lanes, so when you're looking at from top, you can measure these nicely. But as you go towards an oblique view, looking at these from a very oblique lines of sight, you will miss a lot of this. And what you will really see is what comes out of these depressed areas here. So more like a canopy effect. That's something that you will measure. And due to foreshortening, you will kind of cancel the bipolar canopy that you see. So an analogy one can think of is that, well, in these canyons, you can see the river only from a certain angle above it. And as you go from a very oblique projection, you can only see the mouth of the canyon, but not the river. So something like that is a fundamental limitation. And the field-free plasma of the granules is kind of blocking all the signal that you would have seen from the Stokes parameters. So there are these things that we wanted to study more. And I think this kind of tells us that the only way to really measure these accurately is to look above, go above the poles and measure it from there. So go out of the ecliptic plane. This is just the simulations that we use. This is a stagger simulations of Whiteson magnetic network. And so we're using these simulations, synthesize the Stokes profiles, in this case, the Gong spectral line, and then generated synthetic magnetograms at different mu values, different lines of sight. So as you can, and then we use center of gravity algorithm to do these kind of simple maps of just the line of sight magnetic field. No instrumental noise was considered. So just like what is the fundamental systematics, irrespective of the noise that is in the instruments. And so here what we are showing is the cut along one of the intergranular lanes is just the profile along one of the intergranular lanes, basically this blue line. So it samples this lane here. And so you'll see that it's color coded in the line of sight angle, the mu value here. So that you see that the strongest flux is measured when you're really at the looking at vertically from above, and the peak flux goes down as you're going away in the inclination. And so If you integrate the area under these curves, you kind of see that the net flux is how it is underestimated line of sight flux as you go towards the limb. And if you typically the people the assumption that people make in these magnetograms is, oh, you can divide it by mu and then get the radial field under the approximation that most of the flux is vertical. And when you do that, you then see that, yeah, you still cannot recover the flux that is lost due to these effects. So this is, again, emphasizing the same result, but in a different way. It shows the histogram of those magnetograms at different mu angles. As you can see that when you are looking at from the top, you have this distribution which goes to very strong fields, and progressively you're missing those strong fields as you go away from the disk center. And even if you apply the mu correction, you cannot recover the strongest fields because they are just hidden, right? And actually you artificially amplify some of the weaker fields because they are not vertical, but you're applying a vertical approximation to them. So these kind of highlight the fundamental limitations in these kind of polar measurements from ecliptic plane. So what I'm saying is even the highest resolution observations, even the highest resolution telescopes like DKIS, they even without any instrumental noise, they will have these problems because of the fundamental this hidden flux in these intergranular lanes. And we really need to go out of the ecliptic to make these observations. There are, of course, Pathfinder mission is Solar Orbiter, which is already going out of ecliptic plane, and when it's at the peak of its inclination, then I think it will provide even better measurements. But there are upcoming missions, Solaris and Firefly. There will be talks in this symposium, I think, in a few days. So look forward to them. So how these missions are designed to measure right from above. And then, of course, another important thing for these deep space missions is to use instruments which are simple in their measurement approach and design and well understood calibration. So I would think heritage design such as Gong and NDI. And I'd like to advertise one of the instruments based on heritage Gong design, which is a compact form of Gong, is the compact Doppler magnetograph. And it's published in this paper here. It shows how low mass, power, and telemetry requirements are there for this instrument and uses very simple approach. So yeah, that's the point I want to put across. And thanks for your attention.
Thanks, Sanjay. Has anyone got any questions? Yeah, Sammy?
Hi, Sanjay. This is Sami. Nice to hear that talk. Great that you have taken up this project. We had been discussing this quite some time ago. And time there is on arXiv, there is a paper by Sinjan et al., Jonas Sinjan, where you did basically the same thing, center to limb variation, but not just looking at individual features near the limb, but also at the center. And the interesting result is that you find you always lose something like a factor of 2 of the flux, irrespective of your spatial resolution when you're near the limb. But at disk center, you can lose even more if you don't have extremely high spatial resolution. And that's got to do with the fact that your profiles are just crazy and you're mixing up as soon as you don't have perfect resolution. You're mixing up profiles, Stokes V profiles with very different properties, and that leads to that loss. But have you written this up? Because I'd like to see it and then compare the two.
Yeah. Unfortunately, I know I haven't written it. I've been writing it for some time. So I did see the paper, but by the time I had already submitted this. But yeah, I would like to continue talking to you about this more. And I think there are probably ways one can think of recovering some of it in terms of modeling the canopy fields in terms of thin flux tubes models. And I mean, but again, it's something that you infer and it's always a model dependent estimation. But yeah, nothing like going out of ecliptic and measuring. Yeah. Yeah, I haven't read it fully, but yeah, I saw that the results are consistent.
Send me the paper once you have it. It'd be okay.
Yeah.
One interested reader, certainly.
Yeah, thank you. Thank you, Sammy.
Right. Are there any final questions? Yeah. One last question.
Hi, Sanjay. This is Dipankar here. So would you like to comment on the polar field measurement we have been traditionally using from Wilcox? Just 1 pixel, and how underestimate it is with your sort of your experience, and also comparing with the Hinode's polar campaign. So we all know that we need Solaris, but just to build the case even stronger, is there any update in how underestimate the Wilcox results are?
So there, I have not looked into those myself, but I have seen that there is a paper, Wang et al. A few years ago, and in which they try to model the spectral line and the saturation effects in the way you position the pass band on the wing. And so they have tried to explain that if you properly sample the line, it reduces the disagreement with open flux. But again, as I said, so many people have tried to explain so many ways in which open flux can be explained. So it's like there are so many knobs that you can turn and find an agreement. But yeah, no, I haven't looked myself, but that's a magnetograph technique, which is like they still use it, but nowadays I think the state of the art is to use full spectral polarimetric profiles and use the fill factor to derive the real magnetic flux. Yeah.
Okay.
But yeah, we were just focusing on the projection. How does it affect, even like regardless of the resolution of the instrument? There is some fundamental limitations. Yes.
Great. So let's thank Sanjay and all the session speakers again.
Thank you.
So that concludes session 2. Are there any announcements or? No. Okay. So apart from that, there's a poster session tomorrow at 10, and then the session starts again at 10:30. Right. Session 3.